For all our satellites, telescopes and scientific breakthroughs, there are still strange signals, missing matter and puzzling patterns we just can't explain. Some of these mysteries have been around for decades, while others are brand new, discovered only because our tools have become sharper and our questions deeper. It's as if the cosmos is daring us to chase its mysteries, and every answer only leads to a new question. Let's explore the oddities and gaps in our understanding that keep scientists awake at night. Where are the universe's missing baryons? For a long time, scientists have been confident about how much normal matter should be in the universe. This kind of matter, called baryonic matter, is the stuff that makes up everything we can see and touch. Stars, planets, gas, dust, even people. It's made of protons and neutrons. But here's the mystery. When astronomers add up all the baryonic matter they can actually find in the universe, about half of it is missing. It's not in stars, not in galaxies, not even in the clouds of gas around those galaxies. It's just gone. Or at least, it seems that way. This mystery came into focus after scientists studied the early universe. When they looked at the light left over from the Big Bang, called the cosmic microwave background, or CMB, they could see clues about how much matter existed when the universe was very young. That early glow told a clear story. There was a certain amount of baryonic matter, and it matched well with the models of how the universe formed. Later, other studies confirmed those numbers. But when telescopes scanned the sky to count up all the visible matter today, about half of it was nowhere to be seen. At first, this was deeply confusing. If this matter was truly missing, it meant something was wrong with our understanding of the universe. But the numbers were solid. The models worked. The measurements of the early universe were consistent across many different methods. That meant the missing matter had to be out there, somewhere. It just wasn't where we expected it to be. The first guesses focused on things like galaxies and clusters of galaxies. Maybe the matter was hidden in very faint stars, or in cold gas that doesn't shine in any wavelength we usually observe. Maybe it was floating far from the center of galaxies, too spread out to detect. But the more researchers looked, the more they realized it wasn't simply a matter of overlooking something obvious. The missing baryons were truly hidden in a way that needed a new approach. Attention then turned to a much larger scale, the space between galaxies. Galaxies are not evenly spread through the universe. They form giant clusters and long thread-like structures called filaments. Between these filaments are vast empty spaces. The whole setup looks like a kind of cosmic web. And scientists began to wonder, what if the missing baryons are hiding in the spaces between galaxies, in this cosmic web? That idea led to the search for something called the warm-hot intergalactic medium, or WIM for short. This is a kind of gas that is incredibly thin and spread out, but it's also extremely hot, hundreds of thousands to millions of degrees. Because it's so hot, it doesn't glow in the usual way. It doesn't shine in visible light, or even in the type of light most telescopes look for. That makes it incredibly hard to detect. But with the right kind of tools, mainly X-ray and ultraviolet telescopes, scientists have been able to find hints of this warm, hot gas. They look for its fingerprints in the light coming from very distant galaxies and quasars. As that light travels through the WIM, it gets slightly changed, absorbing certain wavelengths in a way that can be measured. These tiny signals are faint and tricky to spot, but they've given scientists growing confidence that much of the missing baryonic matter might really be hiding in this thin, hot web between galaxies. Some of the most important clues came from observations using the Chandra X-ray Observatory and the XMM Newton satellite. These observatories looked for subtle signals of ionized oxygen and other elements in the WIM. Each successful detection added another piece to the puzzle, and over time a picture began to form. If all the WIM gas discovered so far is added together, it starts to close the gap. It's not a perfect match yet, but it's close enough to suggest that the missing baryons may not be missing at all. They're just very well hidden. Even more recent studies have used techniques that stack many observations together. This method combines light from hundreds or even thousands of distant sources, helping to amplify the tiny signals from the WIM. These efforts have shown even stronger evidence that this warm hot gas exists across the cosmic web, and that it holds a significant amount of the universe's missing matter. But while the WIM is the leading suspect, it might not be the whole story. Some scientists think that there could be baryonic matter hidden in even stranger places. Maybe there are clouds of cold, neutral hydrogen far beyond the edges of galaxies, too cool to glow and too faint to see. Or maybe the matter is in forms we don't know how to look for yet, particles or structures we haven't even imagined. There's also the possibility that some baryonic matter is hiding in the halos around galaxies. These halos are made of gas that surrounds galaxies like a kind of invisible cloud. In recent years, scientists have begun to explore these halos using a method called quasar absorption lines. By studying how light from distant quasars passes through a galaxy's halo, researchers can map the gas and get an idea of how much matter is there. These studies suggest that galactic halos may contain more baryonic matter than once thought. As technology improves, so do the chances of finding more of this hidden matter. New space telescopes, better sensors, and more powerful data analysis tools are allowing researchers to peer into regions of space they could never study before. If we can find this missing matter, it helps confirm that our models of the universe are right. If we can't, then something important is missing from those models, and that could point the way to brand new physics. Right now, the evidence seems to show that the baryons are not truly gone. Piece by piece, observation by observation, scientists are closing in on them. The Hubble Tension, one constant, two universes. For over a century, scientists have known that the universe is expanding. That discovery, first made by Edwin Hubble in the 1920s, changed how we see the cosmos. Instead of being fixed and unchanging, the universe is growing, stretching out in every direction. Galaxies are moving away from each other, and the space between them is getting bigger all the time. This rate of expansion is measured by something called the Hubble constant. But in recent years, a strange problem has appeared. Different methods of measuring the Hubble constant give different answers, and the gap between them isn't going away. It's getting more puzzling with time. To understand the issue, we have to look at how these measurements are made. There are two main ways to calculate the Hubble constant. One way looks at nearby parts of the universe. It uses stars and galaxies that are close enough for us to see in detail. The other way looks at the early universe, using the light from just after the Big Bang. Each method is backed by careful observations and solid science, yet they produce different results. That disagreement is what scientists now call the Hubble Tension. The first method, the one using nearby objects, is more direct. It starts by measuring distances to stars in our own galaxy, particularly stars known as Cepheid variables. These stars pulse in a regular way, and their brightness tells us how far away they are. Cepheids act like cosmic yardsticks. Once the distance to these stars is known, scientists can move on to galaxies that host both Cepheids and supernovae. This creates a chain, a ladder of distance markers that reaches out into the universe. By comparing how far away a galaxy is with how fast it appears to be moving away from us, scientists can calculate the Hubble constant. This is what the Hubble Space Telescope has been doing for years. It gives a value for the Hubble constant of about 73 kilometers per second per megaparsec. That means for every 3.26 million light-years you go out into space, the universe expands by an extra 73 kilometers per second. The second method is different. Instead of measuring things close by, it looks far into the past, almost 14 billion years ago, to the time shortly after the Big Bang. The light from that early period, aka the CMB, still travels through the universe today. Satellites like Planck have studied this ancient light in great detail. It tells us what the universe was like when it was just 380,000 years old. From that early picture, scientists can use models to calculate how the universe has expanded since then. These models take into account the kinds of matter and energy in the universe, like dark matter, regular matter, and dark energy, and how they influence expansion over time. Using this method, scientists get a Hubble constant of about 67.4 kilometers per second per megaparsec. That's significantly lower than the value from nearby stars and galaxies. This difference, roughly 6 kilometers per second per megaparsec, might not sound like much. But in science, especially in something as precise as cosmology, it's a big deal. The difference is larger than the margin of uncertainty. That means something is likely wrong with the way we understand the universe, or at least with one of the methods we use to measure it. Scientists have checked both methods again and again. They've used different stars, different galaxies, different techniques. They've tried to find mistakes or overlooked problems in the data. But so far, nothing has explained the tension. Both methods seem to be accurate, and yet both give different answers. This has led to some surprising ideas. Maybe there's something missing from the standard model of the universe. That model, called lambda CDM, has been very successful. It explains the effects of dark energy, represented by the Greek letter lambda, and cold dark matter, that is CDM. It matches observations of the CMB, galaxy formation and more. But if the Hubble tension is real, maybe lambda CDM isn't complete. Perhaps something strange happened in the early universe that we haven't accounted for. There might have been a new kind of particle, something that existed for only a short time after the Big Bang. This extra particle could have affected how fast the universe expanded back then. That would change the prediction of the Hubble constant from the early universe's point of view, bringing it closer to the value we get from nearby observations. Other scientists are exploring the possibility of a new kind of dark energy. The dark energy we know about is thought to be constant. But what if dark energy behaved differently in the past than it does now? A changing form of dark energy could affect how the universe expanded at different points in its history. That, too, might explain the different values of the Hubble constant. Some think the answer could lie in the structure of the universe itself. Maybe our region of the universe is a little different from average. Perhaps we live in an area that's slightly underdense, meaning it has less matter than the universe as a whole. That could affect how fast things appear to be expanding around us. There's also the possibility that there's something wrong with the tools we use. Maybe there are unknown biases in how we observe Cepheid stars or supernovae. Or perhaps we're missing some subtle effect in the way early light travels through the universe. This tension has become one of the most talked about problems in modern cosmology. New experiments are being designed to help solve it. The James Webb Space Telescope, or JWST, is being used to make even more precise measurements of Cepheid stars and other distance markers. Future missions like the Euclid Telescope and the Nancy Grace Roman Space Telescope will also provide new ways to test the expansion of the universe. The primordial lithium problem. Right after the Big Bang, the universe was hot, dense, and full of energy. In the first few minutes, it cooled just enough for the first atomic nuclei to form. This short but important time is called Big Bang nucleosynthesis. It lasted only about 20 minutes, but in that small window, the universe formed the first elements. These were not heavy elements like carbon or oxygen, but the lightest and simplest ones: hydrogen, helium, and lithium. Scientists can work out how much of each of these elements should have been made during that time. The math is based on the laws of physics, the known behavior of particles, and how fast the universe expanded. The results of these calculations have matched what we see in the universe, at least for the most part. The expected amounts of hydrogen and helium are almost exactly what we measure in old stars and galaxies. But lithium is a different story. There's far less lithium in the universe than there should be. This strange mismatch is known as the primordial lithium problem. The Big Bang theory tells us that for every billion hydrogen atoms, there should be about one helium atom, and for every 10 million helium atoms, there should be 1 lithium atom. These numbers come from models that have stood the test of time. They've been checked and rechecked using different kinds of data, but when scientists look at ancient stars, especially the oldest ones in the Milky Way, they find only about 1/3 as much lithium as expected. These old stars, known as population 2 stars, are very low in heavy elements. That makes them perfect places to check for original Big Bang material. These stars formed early, when the universe was young and hadn't yet gone through many cycles of star birth and death. In theory, they should contain the original mix of elements created right after the Big Bang. But again and again, the amount of lithium found in them doesn't match the numbers predicted by Big Bang nucleosynthesis. Lithium isn't very stable in the extreme heat and pressure inside stars. If the surface of a star mixes with the deeper, hotter layers, lithium can break apart and disappear. So, some scientists have suggested that these ancient stars might have stirred their contents in a way that destroyed some of their lithium over time. However, this idea has problems of its own. If all these old stars lost their lithium in the same way, you'd expect to see small differences from star to star. Some stars might have more lithium left, others less. But that's not what we see. Many of the stars seem to have about the same amount of lithium, as if the level had been set in stone from the beginning. That makes the destruction idea less likely, or at least incomplete. Another theory is that something went wrong in the early universe, something that changed how lithium was made in the first place. Maybe the particles we know about behaved differently in the extreme conditions after the Big Bang. Or perhaps there were unknown particles that changed the balance of reactions during nucleosynthesis. Some theories suggest the presence of dark matter particles that could have interfered with the normal creation of lithium. Others have wondered if the problem lies in how we observe and measure lithium in stars. Measuring the makeup of a star is not easy. Scientists use light from stars to work out which elements are present. Each element leaves its own fingerprint in the spectrum of starlight. But if a star's surface has changed in ways we don't fully grasp, maybe due to magnetic fields or unusual mixing, it could throw off the results. Maybe we're just not seeing the lithium that's really there. To try to get around this, some astronomers look for lithium in places other than stars. They've searched for it in interstellar gas, in the material between galaxies, and in young stars that haven't had time to lose much lithium. These efforts give mixed results. Sometimes the amount of lithium is closer to the expected value. Other times, the same problem shows up again: too little lithium. There's also the question of lithium-6, a lighter and much rarer form of lithium. The Big Bang should have made only tiny amounts of lithium-6, while most of the lithium should be lithium-7. But in a few cases, scientists have claimed to detect more lithium-6 than expected. That would be strange, and it could point to something happening in the early universe that we don't yet understand. However, these measurements are very difficult and debated. Not all researchers agree that the extra lithium-6 is really there. Some new ideas take a completely different approach. Instead of focusing on what happened during the Big Bang, they ask whether something in the physics of atoms or particles has been misunderstood. Could there be an unknown decay process where lithium slowly turns into something else? Could the rules of nuclear reactions change under conditions we haven't yet tested? These are deep questions, and answering them may take new kinds of experiments, possibly in particle accelerators or with more powerful telescopes. The mystery of missing lithium might also be connected to other cosmic problems. If there's a hidden piece of physics that affects lithium, it might also help explain why dark matter is so hard to detect, or why the Hubble tension exists. In this way, the lithium problem could be a small piece of a much larger puzzle that points to a deeper layer of truth about the universe. Dark matter or modified gravity, the debate that won't die. When scientists look at galaxies, they find that the stars at the edges are moving too fast. According to the laws of gravity we know, these stars should be flying off into space, but they're not. They stay right where they are, circling the center of the galaxy like clockwork. It's as if something invisible is holding them in place, something with mass, but not light, something we can't see, but can feel through gravity. This invisible something was given a name: dark matter. Scientists came up with the idea to explain why galaxies act the way they do. The stars and gas we can see don't have enough mass to account for the strong gravity needed to keep galaxies together. So the idea is that there must be more matter out there, hidden from view, some kind of dark matter that doesn't give off light or energy but still has weight. It's like the universe is filled with a ghostly substance that surrounds and shapes the things we can see. The concept of dark matter goes back nearly a century. In the 1930s, astronomer Fritz Zwicky studied a cluster of galaxies and noticed the galaxies were moving so fast that the whole cluster should have flown apart. He guessed that there must be extra mass in the cluster, something unseen, that provided the gravity to hold everything together. Later, in the 1970s, Vera Rubin and Kent Ford found similar problems in the rotation of individual galaxies. Their work showed that the stars in spiral galaxies don't slow down as they move outward from the center. Instead, they keep spinning at about the same speed, even far from the core. That only made sense if each galaxy was surrounded by a huge, invisible halo of matter. Over the years, the evidence for dark matter has grown. It doesn't just explain galaxy rotation, it also helps explain how galaxies formed in the first place, why galaxy clusters behave the way they do, and why the cosmic web of the universe looks the way it does. Models of the early universe that include dark matter match what we see in the CMB. Without dark matter, the math falls apart. With it, everything fits together. But here's the problem. We've never seen dark matter directly. We can't touch it, measure it in a lab, or even be sure it exists. No one knows what it's made of. It doesn't absorb light, reflect it, or give off any heat. It only shows itself through gravity. That's led some scientists to ask, what if there is no dark matter at all? What if the problem isn't with the matter, but with the math? This is where modified gravity comes in. The idea is that maybe gravity doesn't work the way we think it does, at least not on large scales. Maybe the laws of motion and gravity, which work so well for planets and stars, start to break down when we look at galaxies and clusters. If that's true, we wouldn't need dark matter to explain what we see. We'd just need a better understanding of gravity. One of the most well-known alternatives is called MOND, which stands for Modified Newtonian Dynamics. It was proposed in the 1980s by physicist Mordechai Milgrom. MOND suggests that at very low accelerations, like the ones you find at the edges of galaxies, gravity acts differently than Newton predicted. According to MOND, gravity becomes stronger than expected in these conditions, which could explain why stars at the edge of galaxies move so fast without flying off. It removes the need for dark matter by changing the rules of the game. MOND has had some success. It can explain the rotation curves of many galaxies with surprising accuracy. In fact, in some cases, it does better than dark matter models. But it struggles in other areas. MOND doesn't always explain what we see in galaxy clusters or in the early universe. It also doesn't fit well with general relativity. And when it comes to the CMB, dark matter still does a better job. There are more advanced versions of modified gravity as well. Some theories try to tweak Einstein's equations, adding new terms or forces. Others suggest that gravity might leak into other dimensions, or that space-time behaves differently over long distances. These models are complex, and many of them require new particles or forces we haven't yet found. But they show that the question is still open. We can't yet say for sure whether dark matter is real or whether our picture of gravity is incomplete. One famous case that seems to favor dark matter is the Bullet Cluster. This is a pair of galaxy clusters that collided in space. When scientists looked at the Bullet Cluster, they saw that most of the visible matter, the gas and stars, had been slowed down and pushed around by the collision. But the mass, as measured by gravity, seemed to pass straight through. The gravity map, made using gravitational lensing, showed that most of the mass was not where the gas was. It was off to the sides, where the dark matter halos would be. This looks like a direct sign that there's invisible mass separate from the ordinary matter. Supporters of dark matter see the bullet cluster as strong proof that dark matter is real. But those who favor modified gravity argue that this event could be explained in other ways, or that the gravity models used to interpret the lensing might be missing something. It's one of many points where the debate gets intense. Meanwhile, scientists are still trying to find dark matter directly. They've built detectors deep underground to look for rare interactions between dark matter particles and normal matter. They've scanned the skies for hints of dark matter breaking apart or colliding. They've tried to create it in particle accelerators like the Large Hadron Collider. So far, nothing has turned up. This silence has raised doubts. If dark matter is real, why haven't we found it yet? Could we be looking in the wrong place? Are we using the wrong tools, or is it simply not there at all? The debate continues, and neither side is giving up. Some researchers think we just need to wait. The discovery of dark matter might be just around the corner. Others believe we're at the edge of a major shift and that new physics will be needed to explain what we see. For now, both dark matter and modified gravity remain on the table. Each has its strengths and weaknesses. As we look deeper into the cosmos, we may one day find out which is true, or whether the answer is something else entirely. The Great Void. Why some cosmic voids are too empty to explain. When we look at the universe on a very large scale, it doesn't seem random. Galaxies form clusters, and those clusters link together like a web. These long filaments of matter stretch across space, with dense knots where galaxy clusters sit. Between these strands is space that looks almost completely empty. These are known as cosmic voids. They're vast regions of space where there are hardly any galaxies at all. Cosmic voids can be millions of light years across. In some ways, they are the quietest, loneliest places in the universe. While galaxies are busy and bright, full of stars, dust, and gas, these voids are still and dark. Scientists have long believed that voids formed naturally as gravity pulled matter together into the filaments and clusters, leaving behind regions with less material. The matter moved from the less dense areas to the more dense ones, making the voids even emptier over time. This is what standard models of the universe predict, but some of these voids are far larger and emptier than the models say they should be. The distribution of galaxies across the sky doesn't always match the predictions of computer simulations. There are parts of the universe where galaxies seem to be missing altogether, on a scale that's hard to explain. These are not just regular voids, they are supervoids. One of the most talked about cases is the so-called cold spot in the CMB. This cold region was discovered by the Wilkinson Microwave Anisotropy Probe, or WMAP, and confirmed by the Planck satellite. Most of the CMB is very smooth, with tiny fluctuations in temperature, but the cold spot stands out as unusually large and colder than expected. Some scientists wondered if a large cosmic void could be responsible. If a photon from the CMB passes through a huge underdense region, it can lose energy. This is due to something called the integrated Sachs-Wolf effect. The idea is that the photon's path through a supervoid could stretch space enough to cool it slightly. In 2015, astronomers found evidence of a supervoid in the same part of the sky as the cold spot. It was one of the largest ever discovered, about 1.8 billion light-years across. But even a void that size shouldn't be able to cause such a strong cold signal. When researchers ran simulations, the numbers didn't add up. The cold spot was too cold, and the void was too empty. The void didn't seem big enough or deep enough to explain the signal. This has led to a growing mystery. If it wasn't caused by a void, what else could it be? Some scientists think the cold spot could just be a statistical fluke, an unlikely patch of sky that happens to look strange by chance. Others wonder if it might be evidence of something deeper. Maybe our models of how matter spread out after the Big Bang aren't quite right. Maybe we're missing something important about how gravity shaped the early universe. Or maybe it's a clue to something entirely new. The mystery of large voids doesn't end there. Surveys of the sky, like the Sloan Digital Sky Survey and the Dark Energy Survey, have mapped more of these empty regions. Some voids are found close together, forming chains of emptiness. Others seem to exist in places where we'd expect to see more structure. Why are some voids so unusually empty? Could dark energy or some unknown force be pushing matter away more strongly than expected? Could different parts of the universe be expanding at slightly different rates? Another idea is that these supervoids could be shaped by massive events in the early universe, fluctuations in density that go back to the first seconds after the Big Bang. If certain regions started with less matter, they might have stayed empty as the rest of the universe formed stars and galaxies. But the CMB, which shows the early universe, is mostly smooth. There aren't big enough ripples in it to explain such deep modern-day voids, unless, of course, something changed afterward. One possibility is that the laws of physics might have behaved differently in some parts of space. This might sound strange, but some theories suggest that different regions of the universe could have slightly different values for fundamental constants, things like the strength of gravity or the mass of particles. If true, that could mean that some parts of the universe are more prone to forming galaxies, while others remain mostly empty. But so far, there's no direct proof that the laws of physics change across space. Another idea comes from theories about inflation, the rapid expansion of space just after the Big Bang. Inflation might not have been perfectly even. Some areas could have expanded more than others, creating large patches with very low density. These might be the places we now see as supervoids. If true, they could carry clues about how inflation happened, and whether it left behind signs of other universes beyond our own. There's also growing interest in the way voids might help test dark energy. Because voids are underdense, they respond more strongly to this outward push. That makes them sensitive indicators of how space itself is changing. By measuring how voids grow and evolve over time, scientists hope to learn more about what dark energy really is. But again, the results aren't always easy to explain. Some voids appear to grow faster than expected or seem too empty for their size. In some studies, scientists have also looked at how light bends around voids, a process called gravitational lensing. Normally, massive objects like galaxies bend light, pulling it toward them. But voids can do the opposite. They can stretch and distort light by the absence of mass. These anti-lensing effects can help map the shape of voids in detail. With more sky surveys and better telescopes, researchers are now able to study voids in greater detail than ever before. But the more they look, the more surprises they find. Some voids line up with strange signals. Others sit in places where we'd expect more matter. Still others defy the rules we've written, based on the known behavior of gravity and expansion. The Axian Mystery. Are ghost particles hiding in the cosmic dark? In the search for what makes up the invisible parts of the universe, scientists have come up with many ideas. One of the most curious is a particle that we have never seen, never touched, and may never be able to detect directly. It's called the axion. Though no one has ever found one, axions are becoming one of the most talked about answers to some of the universe's biggest mysteries. The idea of the axion started with a problem deep inside atoms, in the world of quantum physics. That problem is known as the strong CP problem. In simple terms, this is about why certain parts of physics, like the strong force that holds atomic nuclei together, don't seem to break certain rules, even though they easily could. According to the math of particle physics, there's no reason why atomic forces shouldn't violate something called CP symmetry, which has to do with how particles behave when flipped or reversed. But when we look at the real world, we see that this symmetry is never broken in this way. It's as if nature goes out of its way to avoid it. To fix this puzzle, physicists Roberto Paci and Helen Quinn proposed a new idea in the late 1970s. They added a kind of built-in correction system to the laws of physics, something that would keep the symmetry intact. And this system came with a new kind of particle, the axion. The axion would be incredibly light, would barely interact with other matter, and would be almost invisible. It wouldn't glow, it wouldn't bounce off anything, and it wouldn't be stopped by ordinary matter. In fact, trillions of axions could be flying through you right now, without you ever noticing. That strange behavior is exactly what makes the axion interesting, because even though it came from a problem in particle physics, it might also solve a mystery in astronomy: dark matter. Dark matter doesn't shine, doesn't reflect, and doesn't absorb light. That's a lot like how axions are expected to behave. What makes axions different from other dark matter candidates is their incredible lightness and how they might behave on a large scale. Unlike heavier particles like the hypothesized WIMPs or weakly interacting massive particles, axions might form a kind of invisible wave that fills all of space. In this picture, dark matter isn't a bunch of heavy particles bumping into things, but a soft, quiet ocean of tiny ghost particles washing through the universe. Because they hardly interact with anything, they slip through detectors like wind through a net. Still, scientists are trying. One method involves giant magnets. This is based on a theory that axions could sometimes turn into photons if they pass through a strong magnetic field. If that's true, then we might be able to coax axions into revealing themselves by setting up the right kind of trap. One of the best-known axion experiments is called ADEMEX, the Axion Dark Matter Experiment, housed in a quiet lab in Washington State. The setup uses a powerful magnet and an ultra-sensitive microwave detector. The idea is that if an axion enters the chamber and transforms into a photon, the detector will catch the faintest signal. So far, the experiment hasn't found any axions, but it has ruled out some possibilities and helped narrow the search. Other efforts, like the CAST experiment at CERN, are looking for axions coming from the Sun. The theory goes like this: deep in the core of the Sun, axions might be created in huge numbers. They then fly out in all directions, passing through space, Earth, and detectors. CAST uses a strong magnet taken from an old particle accelerator, turned into a kind of telescope, to try and catch axions turning into X-rays. Again, no definite axions have been seen, but each experiment adds more knowledge to where they might be hiding. There are also ideas that the early universe may have been filled with axions. If that's the case, then they might have left subtle clues in the CMB. Their presence could affect how galaxies formed, how matter clumped together, and how light travels across space. These signs would be incredibly faint, but scientists are developing tools to try and detect them. According to theory, in the presence of a rotating black hole, axions might clump together and form a kind of giant invisible cloud around the black hole, sapping its spin energy over time. These clouds might affect how gravitational waves look when black holes merge, creating patterns that we could recognize if we know what to look for. Because of how they might respond to magnetic fields, researchers are building tools that could scan for their effects in very specific frequency ranges. These devices are cooled to near absolute zero to reduce noise and make it easier to hear the faint whispers that axions might produce. This field of study is growing quickly, with new experiments planned around the world. There's another strange twist to the axion story. Some versions of string theory, the idea that the universe is made up of tiny vibrating strings, predict not just one kind of axion, but hundreds or even thousands of them. These particles could have different masses, different strengths, and could fill the universe in layers. Some might be relics from the early universe, while others could have formed later. If that's true, then dark matter might not be made of just one kind of axion, but a whole hidden world of them. The reason axions matter so much is that they offer a way to connect the smallest scales of physics, the inside of an atom, with the largest scales, the whole universe. They tie together unsolved problems in quantum theory and astronomy in a way that's rare. If they're real, they could tell us how nature balances its forces, why matter formed the way it did, and what fills the darkness between the stars. For now, though, the hunt continues. Across the world, in labs cooled to near zero, inside mountains, and even under the earth, detectors wait quietly. They are listening for the faintest flicker of a ghost particle that may have been hiding in plain sight since the beginning of time. The Flyby Anomaly, when Earth's gravity doesn't play by the rules. It begins with a spacecraft flying past Earth to gain speed, a maneuver called a gravity assist. Engineers have used this trick for decades. By swinging close to a planet, a spacecraft can borrow a bit of its motion, speeding up or changing direction without using much fuel. It's a clever way to travel farther into space without carrying extra weight. It's also something we understand very well. At least, we thought we did. In some of these flybys, after passing Earth, the spacecraft would move slightly faster than it should have been. Not by much, just a few millimeters per second. But in the precise world of space travel, that matters. Even the smallest unexpected change is a red flag. It means something's off in the math, or in the universe. The first real clue came in 1990, when NASA's Galileo spacecraft flew by Earth. It was headed for Jupiter and needed a speed boost. The flyby went as planned, but after careful tracking, scientists noticed it moving just a little faster than predicted. It wasn't a huge deal at the time. Maybe it was a tracking error. Maybe it was just noise in the data. But then it happened again. The Near spacecraft, launched to study an asteroid, flew past Earth in 1998. This time, the anomaly was even clearer. It had gained about 13 millimeters per second, more speed than expected. Again, small, but not small enough to ignore. Other spacecraft showed the same strange pattern. Rosetta, Cassini, Messenger. Some gained speed, others didn't. Sometimes the effect was bigger. Sometimes it didn't appear at all. There was no clear pattern at first, but the fact that it kept happening raised more questions. These were not one-off glitches. Something was happening during these flybys, and no one could fully explain it. Scientists looked at everything. They checked tracking systems. They checked the shape of Earth's gravity field. They checked atmospheric drag, solar radiation pressure, and even the movement of the oceans. Nothing seemed to fully account for the effect. The spacecraft were being tracked with incredible precision, using radio signals bounced off Earth and returned by the spacecraft. These signals let engineers measure speed changes as small as a fraction of a millimeter per second. And yet, in these flybys, something didn't line up. One pattern did begin to emerge. The anomaly seemed to depend on the angle at which the spacecraft approached Earth. If it came in at a steep angle and left at a different one, the effect was more noticeable. It was almost as if the way the spacecraft passed over Earth's rotating surface mattered. That led some to wonder, could Earth's rotation be playing a role in this? Could it be twisting space in some subtle way? This brought up the idea of frame dragging. In general relativity, massive spinning objects like Earth can slightly drag space and time around with them. It's a tiny effect, but it's been proven by experiments like Gravity Probe B. Could this dragging be affecting flybys in a way we hadn't fully modeled? Maybe, but frame dragging is incredibly small, and it wasn't enough to explain the extra speed. Other ideas were tossed around. Could dark matter be clumped near Earth, affecting gravity in ways we don't yet understand? That seemed unlikely, since dark matter should be spread out, not gathered close to planets. Could there be some new force, a slight push or pull that only shows up under certain conditions? That was even harder to test. One of the more down-to-earth explanations suggested that the anomaly might not be a real change in speed at all. Instead, maybe it was just a shift in how we measured the spacecraft's motion. This would mean the anomaly came not from physics, but from the way signals traveled between Earth and the spacecraft, perhaps influenced by small time delays, signal paths bending through space, or even hidden errors in how Earth's rotation affects those signals. In this view, the spacecraft isn't speeding up, it just looks like it is, because of something happening to the light or radio waves we use to track it. It's a subtle idea, and it's hard to prove. It means the anomaly could be hiding in the details of how we measure speed, not in the motion itself. To test that, some researchers began simulating signal paths with extreme precision, accounting for how light travels through space near Earth, including relativity effects. They built new models of Earth's shape, gravity field, and rotation to see if these tiny changes could account for the unexpected speed gains. Some made progress. Others found the anomaly still stubbornly present. Another idea explored whether Earth's gravitational field might not be fully smooth or perfectly modeled. The planet isn't a perfect sphere. It bulges at the equator. It has mountains and valleys, and mass shifts slightly over time due to tides and other forces. Could small features in this complex shape, combined with the spacecraft's exact path, be producing the effect? Some teams also considered the spacecraft themselves. Could heat from onboard electronics be pushing against the spacecraft ever so slightly? When heat escapes in space, it creates a tiny thrust. This effect is known to have altered the paths of some probes, like the Pioneer spacecraft. But in the case of the Flyby Anomaly, the speeds involved didn't match what heat would produce, and the effect seemed tied more to flyby geometry than to the spacecraft's own systems. There hasn't been a confirmed case of the Flyby Anomaly since 2009, partly because spacecraft don't do Earth flybys as often now, and because engineers sometimes adjust their tracking methods in ways that might wash out the effect. But the mystery hasn't been forgotten. It still shows up in papers, quietly debated, quietly studied. Some think it may eventually fade away as a data artifact, something that disappears once we model all the forces more precisely. Others suspect it could be a hint of new physics, hiding in plain sight. A ripple in our understanding of motion, energy, or space itself. The kind of clue that over time leads to deeper discoveries. Right now, the Flyby Anomaly sits in a strange place. It's not big enough to shake our entire understanding of physics, but it's also not small enough to ignore. It's like a whisper in a room full of noise. Easy to miss, easy to doubt, but impossible to forget once you've heard it. Saturn's Hexagon, a persistent atmospheric puzzle. It was first seen clearly in the early 1980s. NASA's Voyager spacecraft flew past Saturn and snapped images of the gas giant's North Pole. Among the many strange sights in Saturn's thick, fast-moving clouds, one feature stood out. There was a storm circling the pole, but not just any storm. It was shaped like a hexagon, a six-sided polygon spinning steadily in a place where no solid ground exists, something straight-edged and stable in a world built from winds. At first, scientists were cautious. Could it be an illusion caused by image processing? A camera error? Maybe shadows or lighting were playing tricks, but later, missions confirmed it. In 2006, the Cassini spacecraft arrived at Saturn and began sending back detailed images of the strange shape. There it was again, clear, sharp, and even more puzzling than before. A massive hexagon, wider than 2 Earths across, encircling the planet's North Pole like a giant geometric crown. And it wasn't fading, it wasn't drifting. It just stayed there, turning slowly with Saturn's atmosphere, year after year. The shape is not made of clouds frozen in place. It's made of motion, of wind patterns flowing in such a way that the edges form a near-perfect hexagon. Each side is about 13,800 kilometers long. The winds along its path move at speeds near 320 kilometers per hour, but instead of forming a circular jet stream, like we see on Earth, the winds bend into sharp angles, creating a steady, six-sided figure. On a gas planet like Saturn, nothing is supposed to stay this neatly arranged. Storms change shape, wobble, or break apart. Even Earth's strongest jet streams twist and snake. Yet here was a storm with corners, clean, symmetrical corners, lasting not for days or months, but decades. The mystery drew in atmospheric scientists, physicists, and fluid dynamics experts. Some began to test models in labs here on Earth. In one experiment, researchers spun a tank of liquid and placed a spinning object in the center. By adjusting the speed of rotation and temperature differences, they were able to create polygon shapes, triangles, squares, and eventually hexagons. The fluid naturally shaped itself into patterns under the right conditions. This showed that stable shapes can form in rotating systems with differences in speed or temperature between layers. It meant Saturn's hexagon might be a kind of standing wave. a natural pattern that forms and holds in place under the right balance of forces. On Earth, similar waves happen in rivers or even air masses, but they don't usually form geometric patterns so large or so perfect. On Saturn, the difference might come from scale. The planet is enormous, its atmosphere deep and layered. The forces shaping the hexagon are happening across thousands of kilometers. The jet stream that forms the edges of the hexagon is believed to rotate faster than the winds inside or outside it. This mismatch in speed, combined with Saturn's rapid rotation and low friction, might create a natural balance that locks the pattern in place. Cassini's close-up images added more detail. The storm had depth. The clouds inside the hexagon moved in different ways than those outside. There was a central vortex, another storm, sitting directly over the pole, swirling like a hurricane eye. And the hexagon itself was not a flat outline. It had vertical structure, with layers of clouds rising and falling along the edges. Infrared images showed that the shape reached deep into the atmosphere, not just the upper layers. What kept scientists puzzled, though, was how persistent it all was. The hexagon never unraveled. It didn't fade with the seasons. Saturn takes nearly 30 years to orbit the Sun, so one season on the planet lasts about 7 Earth years. During Cassini's time at Saturn, scientists watched as the North Pole moved from winter into spring and then into summer. The lighting changed, the winds shifted slightly, but the hexagon remained. Cassini also captured images showing that the hexagon changed hue over time, from a bluish tint during winter to a more golden color during summer. This may be due to sunlight triggering chemical changes in the upper atmosphere or small particles being added to or removed from the air. How can something this structured survive in an atmosphere as chaotic as Saturn's? The planet has storms bigger than Earth, including the Great White Spot, a massive storm that appears roughly every 30 Earth years. Yet none of these events seems to disturb the hexagon. Researchers began to look for analogues elsewhere. Did Jupiter have a similar feature at its poles? The answer seemed to be no. While Jupiter has polar storms and large cyclones, it doesn't form clear polygonal shapes like Saturn's hexagon. It appears that the unique conditions on Saturn, its temperature, wind speeds, rotation, and atmospheric makeup, combine in just the right way to make this happen. Some models suggest that the hexagon could stretch hundreds or even thousands of kilometers down. But without solid surfaces to anchor the pattern, how can it stay aligned for so long? No one knows for sure. Gravity data collected by Cassini on its final orbits hinted that Saturn's atmospheric flows go deep into the planet. That means the hexagon could be just the visible tip of a massive system rotating far below. Others have proposed that the hexagon might be a type of Rossby wave, which also occurs on Earth. These are large waves in a rotating fluid, created by the planet's spin and the way air moves between different latitudes. On Earth, Rossby waves shape the jet stream and sometimes lead to weather patterns that last for weeks. On Saturn, a supercharged version might be forming a permanent standing wave with sharp edges. There's also a more speculative idea. Some scientists have wondered whether the hexagon could be linked to Saturn's magnetic field. The planet's magnetic field is odd. It's more symmetrical than expected. It lines up closely with Saturn's axis of rotation, which breaks some of the usual rules for how magnetic fields behave in spinning bodies. Could there be a link between the field's unusual symmetry and the hexagon's shape? If so, it might hint at something deeper going on inside the planet. But so far, the mystery remains. The hexagon doesn't offer many clues. It just spins, year after year, indifferent to the questions it raises. It's not just the shape that captures attention. It's the fact that something so precise and mathematical can emerge from something so chaotic. A hexagon, floating in clouds, waiting for us to understand how nature carved such order into a world of storms. Lumps in the cosmic microwave background that shouldn't exist. For the first 380,000 years of the universe, everything was too hot and dense for light to travel freely. Atoms couldn't form, and photons kept bouncing off particles like electrons and protons. But as the universe cooled and expanded, atoms began to form, and light was finally able to move through space. That light is what we now call the CMB. When scientists first measured it in detail, they expected it to be smooth, with tiny bumps, small differences in temperature and density. These little bumps would later grow into galaxies, clusters, and the large-scale structures of the cosmos. The CMB map was supposed to be mostly uniform, with only tiny, random fluctuations. But when the first detailed map of the CMB was made in the 1990s by the COBE satellite, and later by WMAP and Planck, scientists found that the bumps weren't entirely random. Some patterns were larger than expected. Some areas were a little too cold or too warm, and not in ways the models had predicted. One of the most puzzling features was the cold spot. It stretches across hundreds of millions of light years, and it's colder than it should be by just a few millionths of a degree, but enough to stand out. And the cold spot isn't the only odd feature in the CMB. There's also what some researchers call the axis of evil. That's a nickname for a set of alignments seen in the CMB map. The largest scale fluctuations, the ones that stretch across the whole sky, seem to be pointing in a particular direction. They're not randomly scattered as expected. Instead, they line up in a way that suggests some kind of preferred axis across the universe. This goes against one of the basic assumptions of modern cosmology, that the universe is the same in every direction when viewed on large enough scales. If the universe really does have a special direction, it would change our understanding of how it formed. Some scientists think the alignment might be a coincidence or a trick caused by the way we collect and clean the data. Earth's motion, the Milky Way's glow, and even instrument noise could leave behind patterns that appear meaningful but aren't. So far, though, those explanations haven't been able to fully erase the strange alignments. Then there are the other, smaller anomalies. Temperature differences that are just a bit too big or arranged in patterns that seem unlikely. One oddity is the difference between the northern and southern halves of the sky. The southern hemisphere of the CMB seems to have slightly more variation than the northern one. In a truly random and balanced universe, both halves should look about the same. Another surprise came when scientists tried to calculate a number called the quadrupole moment. That's a measure of the largest scale variations in the CMB. The number was lower than expected, much lower. It didn't match what simulations said it should be. It was as if the largest waves in the early universe were quieter than they were supposed to be. None of these features are dramatic by themselves. They're small quirks, measured in fractions of a degree, but they matter. The CMB is our most direct view into the early universe. It's like a baby picture of everything, taken just after birth. If something is off in that picture, it could mean our ideas about the Big Bang, inflation, and the growth of the cosmos need to be adjusted or completely rethought. The early universe was shaped by quantum fluctuations, tiny, random changes that were stretched out by inflation. These fluctuations created the seeds for everything we see today. If the CMB shows patterns that don't fit, it might mean that inflation happened differently than we think, or maybe something else entirely was at work. To dig deeper, scientists have turned to simulations, looking at millions of possible universes and comparing them to our own. They try to figure out how likely it is that the CMB we see is just a rare version of a mostly normal universe, or whether it truly hints at something strange underneath. Still, there's no clear answer. Some researchers believe the anomalies are real and demand a new explanation. Others think they're odd, but not meaningful. The problem is that we only have one sky to look at, one version of the universe's early light. That makes it hard to know whether we're seeing something rare or something fundamental. The Simons Observatory and the CMBS-4 mission are being designed to measure the microwave background with even greater precision. These tools might reveal whether the odd features are just noise or signs of new physics waiting to be discovered, but for now, the lumps remain. The cold spot, the axis of evil, the low quadrupole speak in a quiet, stubborn voice, asking questions we can't yet answer. The Ibex ribbon, a celestial band no one predicted. Far beyond the orbit of Pluto, past the reaches of the known planets, lies the edge of our solar system. This border is not a solid wall, but a shifting, invisible boundary where the solar wind, streams of charged particles flowing from the Sun, meets the vast expanse of interstellar space. It is a frontier where the influence of our star fades and the galaxy begins to press in. For decades, scientists imagined this edge would be smooth, shaped like a bubble blown into space. But in 2009, something completely unexpected appeared. That year, a small spacecraft called IBEX, short for Interstellar Boundary Explorer, sent back data that surprised everyone. Instead of a uniform edge, IBEX saw something strange, a long, bright ribbon of energy wrapping around the sky. It was a narrow band where particles were far more energetic than anywhere else along the solar system's edge. Scientists hadn't predicted anything like it. None of the models of the heliosphere, the protective bubble around our solar system, had suggested such a feature could exist. The ribbon was narrow, but it stretched across a huge part of the sky, forming a complete arc. It glowed brightly in the specific type of particles IBEX was built to measure, energetic neutral atoms, or ENAs. These are particles that begin as charged ions in the solar wind but become neutral when they grab an electron, usually from atoms in the interstellar medium. Once neutral, they can travel long distances without being affected by magnetic fields. The ribbon didn't follow the Sun's magnetic field. It didn't line up with the solar wind. And it didn't match any patterns from previous observations of space. It was as if something out there, just beyond the reach of the planets, was shaping a band of energy that had somehow escaped everyone's notice until that moment. Scientists scrambled to explain it. One early idea was that the ribbon marked the direction of the interstellar magnetic field, the field carried through space by the gas and dust between stars. Maybe, the thinking went, the ribbon was a kind of mirror. The solar wind's charged particles would hit the boundary of the heliosphere, bounce off, and then pick up electrons from the interstellar medium, forming ENAs that happened to flow back toward Earth from a narrow region. That region, lined up with the interstellar magnetic field, might be what IBEX was seeing. But this theory required very specific conditions at the edge of the heliosphere. The magnetic fields had to align just right, and the particles had to reflect in a narrow range of directions. Some models could make it happen, but only if all the variables lined up perfectly. That made it feel more like a patch than a real answer. Other ideas followed. Maybe the ribbon was a region where the interstellar medium pressed more strongly against the solar system, forming a kind of shock or compression zone. Or maybe it was a sign that the heliosphere wasn't shaped like a simple bubble after all. Some researchers began to wonder if it was shaped more like a comet, long and trailing, being pushed and pulled by the galaxy's magnetic fields. Perhaps the ribbon was a sign of some unknown interaction between particles and fields, something we hadn't seen anywhere else. Maybe the region beyond the heliosphere was more complex than anyone imagined, filled with shifting currents, twisted magnetic lines, and invisible waves that could shape and focus particles in unexpected ways. As time passed, IBEX kept watching. The ribbon didn't go away. In fact, it seemed to change slightly with time. Its brightness varied and its shape wobbled. These changes followed the solar cycle, the 11-year rhythm of the Sun's magnetic activity. That made sense. The solar wind changes as the Sun becomes more or less active, but it didn't explain why the ribbon was there in the first place. It only showed that the ribbon was somehow connected to the solar system, even though it formed at its edge. Later, another spacecraft joined the search. NASA's New Horizons probe, best known for its 2015 flyby of Pluto, carried a similar detector. It wasn't designed for this purpose, but it could still help. From its distant position, farther from Earth than IBEX, it gave a second look at the ribbon, confirming its shape and location. But the best clues came from two older travelers, the twin Voyager spacecraft. Launched in the 1970s, Voyager 1 and 2 had finally left the heliosphere and entered interstellar space. They carried instruments to detect changes in particle flow and magnetic fields. Although they couldn't see the ribbon directly, They moved through the region beyond the boundary, offering a local view of what Ibex had observed from afar. The voyagers confirmed that the region beyond the heliosphere was anything but simple. The interstellar magnetic field was twisted. The particle environment was active. Waves of plasma and magnetic fluctuations swept past the spacecraft. This seemed to support the idea that the ribbon was tied to the structure of the interstellar magnetic field. But once again, no clear, complete answer emerged. Ibex is still active today, more than a decade after its discovery. It continues to scan the sky for ENAs, watching the ribbon shift and flicker as the solar cycle marches on. Meanwhile, scientists are developing new missions including IMAP, the Interstellar Mapping and Acceleration Probe, which will launch in late 2025. It will give a sharper view of the ribbon and the boundary of our solar system, and maybe, at last, reveal its true nature. Population 3 stars, ghosts of the first light. For hundreds of millions of years after the Big Bang, the cosmos stayed quiet and black, filled only with gas. Then the first stars flickered to life. These ancient stars, the very first to shine, are known as Population 3 stars. They lit up the darkness and began shaping everything that would follow. But in all the years since, no one has ever seen one. Scientists believe Population 3 stars were very different from the stars we see today. Unlike the Sun, which contains heavier elements like carbon, oxygen and iron, these early stars were made only of hydrogen and helium. That's because there were no heavier elements yet. Nothing had made them. The universe had to wait for stars to begin fusing lighter atoms into heavier ones through the process of nuclear fusion. That's why Population 3 stars are so important. They were the first engines of creation. They built the elements we need for life. Every bit of carbon in our bodies, every atom of iron in our blood, every grain of dust on Earth, all of it had to come from stars. And it started with them. These first stars were like cosmic factories, taking in hydrogen and helium and turning them into the building blocks of everything. But even though scientists are sure they must have existed, no one has found a Population 3 star. One reason they're so hard to find is because they didn't live long. These early stars were probably huge, many times more massive than the Sun. Some may have been 100 times heavier. That size gave them short lifespans. Instead of burning slowly over billions of years like our Sun, they used up their fuel quickly, perhaps in only a few million years. When they died, they exploded as supernovae, scattering the new heavy elements they'd made into space. This cycle of life and death seeded the next generations of stars. Later stars, called Population 2 and Population 1, formed from gas clouds that now contained heavier elements. That's why stars we see today are different. They're not pure. They're mixtures, made from gas already shaped by the first stars. The remains of Population 3 stars are in everything, but they themselves are gone. Still, scientists haven't given up. Instead of looking for one of these ancient stars alive today, many are now searching for signs of their past actions. One approach is to look for the chemical fingerprints they left behind. When a massive Population 3 star explodes, it throws heavy elements into space in a very specific pattern. By examining the makeup of old metal-poor stars in the Milky Way, researchers hope to find a match, something that suggests a nearby cloud of gas was once touched by a Population 3 supernova. Some of these searches have shown hints. A few very old stars in our galaxy have unusual chemical compositions. They are rich in lighter elements like carbon, but almost completely lack heavier ones like iron. That could be a clue. These stars might have formed from the gas clouds that were first enriched by the deaths of Population 3 stars. Another method is to look farther away, back in time. Because light takes time to travel, distant objects show us what the universe looked like in the past. Telescopes like JWST are now peering into the early universe, looking for galaxies formed only a few 100 million years after the Big Bang. These galaxies might still carry the light of Population 3 stars, especially if those stars exploded in huge bursts that lit up the sky. Some theories suggest that the earliest galaxies may have glowed with a very distinct kind of ultraviolet light, created by hot, massive stars made only of hydrogen and helium. Recently, scientists using James Webb found galaxies that seem much brighter than expected for their age. Some are wondering if those could contain clues of population 3 stars. The brightness and color of the light don't match what we'd expect from more modern stars. But these signals are hard to interpret, and many factors can affect the light we see. Dust, distance, and other stars can all mix into the signal, making it difficult to isolate the source. The universe is more than 13 billion years old. That means even if we could somehow see one of these stars directly, we'd only catch its light if it came from very early in cosmic history. Most of those stars burned out long ago. Their light would have passed us billions of years ago unless it somehow got stretched or delayed. In some rare cases, a galaxy behind a gravitational lens, where a massive object bends space and focuses distant light, might allow us to see deeper than usual, but even that requires perfect conditions and a bit of luck. Some scientists have proposed building special telescopes to focus just on this problem. These instruments would look for the specific wavelengths of light expected from population 3 stars, especially during their explosive deaths. A few theoretical models suggest these early stars may have ended their lives not as normal supernova, but as pair instability supernovae, massive explosions so large they tear the star apart completely, leaving no core behind. These explosions would produce a unique light pattern. Despite all the challenges, the hunt for population 3 stars continues. Finding one would unlock a key piece of the universe's story. It would confirm our ideas about how the first structures formed, how the elements were born, and how galaxies began to take shape. And so, scientists search the skies for the faintest flickers of stars that haven't shined for billions of years. Galaxies without dark matter, the DF2 and DF4 controversies. In 2018, a group of scientists announced the discovery of a galaxy that seemed to be missing dark matter. It was called NGC 1052 DF2, or just DF2 for short. This galaxy looked fuzzy and faint. It didn't have many stars and it wasn't very dense. But what caught everyone's attention was that the stars inside it weren't moving fast enough. Normally, a galaxy's stars zip around quickly because of the pull of dark matter. But in DF2, the stars moved slowly, as if there wasn't any extra mass holding them together. It was as if someone had switched off the dark matter. That wasn't supposed to happen. According to current models, galaxies form inside clouds of dark matter. The dark matter pulls in gas and dust, which then collapses to form stars. Without dark matter, there shouldn't be a galaxy at all. So DF2 was puzzling. If it really had little or no dark matter, it could mean that something was wrong with the basic picture of how galaxies grow. At first, the reaction was mixed. Some scientists were excited. This was a rare chance to study what a galaxy without dark matter might look like. Others were skeptical. Maybe there was a mistake in the measurements. Maybe DF2 was farther away than thought. Or maybe the stars were being influenced by something else. To find out, the team kept looking. Not long after, in 2019, they found another galaxy like it, NGC 1052 DF4, or DF4. It looked almost the same, faint, ghostly, and full of stars that weren't moving fast enough to need dark matter. Now there were two, and both were located near a larger galaxy called NGC 1052, suggesting that something in this region of space might be affecting their structure. If these galaxies really had almost no dark matter, how did they form? Were they born differently, or had they somehow lost their dark matter later? One idea was that these galaxies might have passed too close to a larger galaxy, which pulled away their dark matter through gravity. In this process, known as tidal stripping, the dark matter halo could be separated from the stars, leaving behind a strange, almost naked galaxy. But for tidal stripping to work, the galaxy would need to move in just the right way, at just the right distance and speed. And even then, stripping away all the dark matter and leaving the stars behind without disturbing them too much seemed difficult. Simulations showed it was possible, but unlikely. Others suggested that maybe the galaxies weren't really dark matter free at all. Maybe the original distance estimate was wrong. If the galaxies were closer than the team thought, their stars would be dimmer and the galaxy would be smaller, which could mean that the stars were moving faster than they appeared. This would change the calculation of how much dark matter is needed. One study re-examined the distance to DF2 and found that it might be a few million light-years closer than first believed. If that were true, then the motions of the stars could be explained with a normal amount of dark matter. But the original team disagreed. They pointed to independent measurements that supported the original distance, including ones based on surface brightness and the types of stars inside the galaxy. This back and forth continued for years. More observations were made. Telescopes in space and on the ground looked at DF2 and DF4 in different ways. Some results supported the idea that the galaxies had little dark matter. Others leaned the other way. It became one of those strange cases in science where both sides had evidence, but no one could completely settle the issue. Still, if these galaxies are real and truly dark matter poor, they could teach us something important about dark matter itself. Most galaxies are thought to be dominated by dark matter, especially small ones. So, finding galaxies that aren't suggests that dark matter isn't always required. It might also help in understanding what dark matter is made of. Some dark matter models predict that it should clump in certain ways, or that it can be pushed or pulled under extreme conditions. Galaxies like DF2 and DF4 could act as natural experiments, helping scientists test these ideas in the real universe. Both DF2 and DF4 belong to a class of objects called ultra-diffuse galaxies. These galaxies are unusual because they spread their stars out over a large area, making them look like ghost versions of normal galaxies. Their low surface brightness makes them hard to spot, and for a long time, no one even knew they existed. Now that they've been found in larger numbers, scientists are trying to figure out where they come from and how they evolve. Maybe galaxies like DF2 and DF4 are rare outliers. Maybe they're just unusual cases that formed under special conditions. But if more are found, especially ones far from massive galaxies that could have stripped away their dark matter, the mystery will deepen. Researchers are searching for similar galaxies in other parts of the sky. With more powerful tools, it may become easier to spot these faint diffuse objects and measure how their stars move. Each new discovery could either strengthen the case for galaxies without dark matter or show that these two were misread. In the meantime, DF2 and DF4 challenge one of the basic assumptions in cosmology, that dark matter is everywhere, silently shaping the cosmos from the shadows. If these galaxies really formed and survived without it, then our understanding of how galaxies work might need to be revised. The paradox of ultra-diffuse galaxies. The first ultra-diffuse galaxies, or UDGs, started showing up in deep images of galaxy clusters. These were surveys that went far beyond what earlier telescopes could see. In 2015, a team using the Dragonfly telephoto array spotted dozens of these galaxies in the Coma cluster. At first glance, they looked like small smudges of light. But when the team measured their size, they realized these smudges weren't small. They were enormous, some as wide as the Milky Way. But they held only a few 100 million stars, while the Milky Way has hundreds of billions. That contrast doesn't make sense under normal rules. Big galaxies usually have lots of stars. Small ones have fewer. But these galaxies were breaking that pattern. They were giants in size, but dwarves in brightness. It was like finding a city the size of New York, with only a few hundred people living in it. This raised a serious question. How do these galaxies even hold together? A galaxy needs gravity to stay intact. The stars must move in a way that keeps them from flying off into space. In most galaxies, that gravity comes from both visible matter and dark matter. With so few stars, UDGs shouldn't have enough gravity to stay bound, unless they have an unusually large amount of dark matter. That's one theory. that ultra-diffuse galaxies are dark matter-rich. Maybe they're normal galaxies that formed in giant halos of dark matter, and for some reason they just never formed many stars. If true, that would make them useful tools for studying dark matter. Since they don't have much going on in terms of bright, crowded star populations, scientists can study the way gravity works in these systems more cleanly. But there's a problem with that idea. Some UDGs, like the DF2 and DF4, appear to have little or no dark matter at all. That throws the whole picture into confusion. If some of these faint giants are full of dark matter, and others are almost empty, then they can't all be following the same rules. There might be more than one type of ultra-diffuse galaxy. Some could have formed in massive dark matter halos, while others formed under very different circumstances. Maybe UDGs were pulled on by other galaxies in a crowded cluster and stretched out over time. Their gas might have been stripped away by hot plasma or by interactions with the cluster's gravitational field. With their gas gone, they couldn't form new stars. Their older stars faded, and the galaxy became dim and ghost-like. But not all UDGs live in crowded clusters. Some have been found in quiet, isolated areas of space. If tidal forces and cluster environments explain only some of these galaxies, then others must have formed another way. Some scientists suggest that UDGs might have formed with large amounts of gas but low rates of star formation. Maybe early bursts of star-making used up the gas too quickly, or perhaps violent supernovae pushed the gas out. Without enough gas left to build more stars, the galaxies stalled. Over billions of years, their stars drifted outward, puffing up the galaxies until they became large but faint. In many cases, the stars in UDGs are spread out in smooth, diffuse patterns. There's not much structure, no bright bulge in the center, no spiral arms, no dense clusters. Some look more like blobs than galaxies, yet others are more organized. A few have disks, and some even show signs of rotation, just like spiral galaxies. It's as if ultra-diffuse galaxies come in many flavors, some more chaotic, some more stable. Astronomers are now using a wide range of tools to try to understand them. Space telescopes like Hubble have helped take sharp images of these faint objects. Ground-based observatories like Subaru and Keck are tracking the motions of their stars to measure how much gravity, and therefore dark matter, they must have. Radio telescopes are looking for hydrogen gas to see if these galaxies still carry the raw materials for future star formation. The search has turned up hundreds of ultra-diffuse galaxies, and the number keeps growing. Some live inside clusters like Coma and Virgo. Others float far away from any other major structure. In 2020, researchers even found one in a cosmic void. That galaxy had stars, structure, and size, but barely any neighbors. One of the most puzzling discoveries came from a group of UDGs that appear to have globular clusters, dense groups of old stars surrounding them. In some cases, the number of these clusters is higher than expected, especially considering how few stars the galaxies have. That could be a clue. Maybe globular clusters formed first in these galaxies and played a role in holding them together early on. Or maybe they're a sign that the galaxies once had more mass, which has since been lost. Why do some of these galaxies spin while others don't? Why do some have gas while others are dry? Why do a few seem to lack dark matter entirely, while others seem full of it? And most of all, what do these odd objects tell us about galaxy formation across the universe? Ultra-diffuse galaxies aren't just smaller or dimmer versions of normal galaxies. There's something else entirely. They exist in a kind of grey zone, too big to be dwarfs, too faint to be spirals, too quiet to be active, and too mysterious to be ignored. As surveys reach deeper into space, more of these ghost galaxies will likely turn up. Some may be relics from the early universe, survivors of ancient cosmic battles. Others may be quiet outliers, shaped by forces we don't fully understand. Their stories are scattered across the sky, waiting to be put together. The Great Attractor, an unseen mass. Drawing the cosmos inward. Out beyond our galaxy, something is pulling us. Not just us, but thousands of galaxies, entire clusters, and all the space in between. They're all moving in one direction, slowly but steadily, as if something enormous is tugging on them from the far side of the sky. It's a motion that stretches across hundreds of millions of light years. Scientists call this pull the Great Attractor, and they still don't know exactly what it is. In the 1970s and 80s, astronomers were mapping out the motion of galaxies using tools that measured redshift, which tells us how fast an object is moving away from us. According to the expansion of the universe, galaxies should mostly be moving outward in all directions, getting farther apart as space itself stretches. But some galaxies weren't just moving outward. They were moving slightly sideways, toward a specific region in the sky. That meant there had to be a large source of gravity in that area pulling on them. But we couldn't see what it was. The area where this mysterious pull seems to come from is in the direction of the constellations Centaurus and Norma. That part of the sky lies behind the plane of our own galaxy, the Milky Way. It's covered by thick clouds of stars, dust, and gas. That region is known as the zone of avoidance because for many years our telescopes couldn't see through it clearly. It was as if we were staring at a curtain, knowing something was behind it, but unable to tell what. Still, something had to be there. Our own Milky Way galaxy is part of a small group of galaxies called the Local Group. This group, along with thousands of others, is part of a larger structure known as the Virgo supercluster. But all of these galaxies, across this massive space, are flowing toward a single point at a speed of over 1 million miles per hour. This motion is called a peculiar velocity. That's a term used for movement not caused by the general expansion of the universe. Peculiar velocities mean something nearby is pulling on an object. The stronger the pull, the more massive the source has to be. Early studies suggested the Great Attractor might be a huge cluster of galaxies hidden behind the Milky Way. Later work added more pieces. One region that came into focus was the Norma cluster, a thick knot of galaxies about 200 million light-years away. It seemed massive enough to have some influence, but not enough to explain the full effect. The pull was just too strong to be caused by a single cluster. The Great Attractor isn't a pinpoint object. It's more like a deep valley in the landscape of space, a region of higher mass where gravity bends everything nearby. Galaxies don't just drift toward it, they fall into it, pulled by the invisible weight. But the deeper scientists looked, the more complicated things became. It turns out the Great Attractor might not even be the biggest force in that part of the universe. Later studies revealed another structure even farther away, the Shapley supercluster. This supercluster is around 650 million light-years from Earth and may contain over 8,000 galaxies. It's one of the most massive known structures in the local universe. Some researchers think the Shapley supercluster might be the real source of the pull, or at least the largest contributor. That brings up the possibility that the Great Attractor might not be a single thing. It could be the combined gravitational pull of several galaxy clusters and superclusters all lying in a chain. These vast structures form a cosmic web. Gravity flows along the strands, pulling matter toward denser regions. What we call the Great Attractor may just be our local piece of this pattern. Still, many questions remain. What exactly lies behind the Milky Way's veil? In recent years, astronomers using infrared and radio waves have started to see through the dust. Telescopes like the Parkes Radio Telescope and the Planck satellite have given us better maps of the sky's hidden regions. One of the challenges is that gravity works on long timescales. The galaxies we see moving today may have started falling toward the attractor billions of years ago. Over that time, the universe has expanded, structures have moved, and mass has shifted. That makes it hard to figure out where the center of the pull actually is, or whether it even exists in a single spot. It's possible that the Great Attractor is made up not just of visible galaxies, but of a huge concentration of dark matter as well. That would explain the strong gravitational force without requiring us to see all the mass directly. Others have suggested the movement of our galaxy group may not be toward a single attractor, but away from a vast empty region, a supervoid, on the opposite side of the sky. That's called the dipole-repeller idea. In this model, it's not just attraction that shapes motion in the universe, but also repulsion from underdense areas. The universe isn't just being pulled by mass, it's also being pushed by emptiness. Whatever the answer, the Great Attractor continues to challenge our understanding of large-scale structure, of motion, and of what lies hidden beyond what we can see. The missing satellites problem: where are the small galaxies? The Milky Way is surrounded by dozens of smaller galaxies, like the Large and Small Magellanic Clouds, and other faint companions scattered across the sky. These are known as satellite galaxies, smaller systems that orbit a larger galaxy, just as moons orbit planets. According to the best models of how the universe works, there should be far more of these small galaxies than we actually see. This is known as the missing satellites problem. Galaxies grow when dark matter clumps together. These clumps are called halos. Gas collects in the center of these halos, cools down, and starts to form stars. Over time, galaxies take shape. Large galaxies like the Milky Way grow by merging with smaller galaxies and pulling them in through gravity. These leftover small galaxies, the ones that don't get completely absorbed, become satellites, still orbiting the bigger system, like remnants of an earlier age. Computer simulations based on this model are incredibly detailed. When scientists simulate a galaxy like the Milky Way, they find that it should be surrounded by hundreds or even thousands of small dark matter halos. If each of these halos hosts a small galaxy, then our sky should be filled with faint companions. But that's not what we observe. When we look around the Milky Way, we see maybe a few dozen satellite galaxies, not hundreds or thousands. Even with deep sky surveys and powerful telescopes, the count falls far short of predictions. This mismatch between theory and observation is the issue. It doesn't just raise a question about small galaxies, it raises doubts about the accuracy of our whole model of galaxy formation. One of the first ideas to explain the gap was that many of these dark matter halos are real, but simply failed to form stars. In other words, the halos are there, but they're invisible, not because they're made of dark matter, but because they never lit up. Tiny halos might not be massive enough to attract and hold on to gas, especially in the early universe when cosmic conditions were harsh. Without gas, they couldn't cool down, and without cooling, stars wouldn't form. That idea gained support when researchers looked at the effects of cosmic reionization. This was a period a few 100 million years after the Big Bang, when the first stars and galaxies pumped out enough radiation to heat the surrounding gas. That heating made it harder for small halos to pull in new gas. If a halo formed before reionization, it might have had time to build a few stars. But if it formed after, it may have stayed dark forever. This could explain why only some small halos seem to host visible galaxies. Another possible answer is that we're simply not seeing all the galaxies that are out there. Many satellite galaxies are incredibly faint. They contain only a few hundred or a few thousand stars, so few that they can easily be missed, even in wide sky surveys. Some of them are spread out across large areas, making them hard to distinguish from the background of stars. These are called ultra-faint dwarf galaxies, and they're right on the edge of what current telescopes can detect. Over the last 2 decades, astronomers have discovered more of these faint galaxies, especially with things like the Sloan Digital Sky Survey. The discoveries helped close the gap between predicted and observed numbers, but not entirely. The missing satellites problem is smaller than it once was, but it's still there. In some simulations, the small galaxies are scattered randomly around the larger galaxy. But in the real Milky Way, some satellites appear to move in a thin, organized, disk-like pattern. That's unexpected. If satellite galaxies formed randomly in dark matter halos, we wouldn't expect them to line up like that. This has led to even more questions about whether the model needs adjusting. In the standard model, dark matter is cold, meaning its particles move slowly and clump together easily. But if dark matter were warm instead, if its particles moved faster in the early universe, then it wouldn't form as many small halos. That could solve the missing satellites problem by reducing the number of small structures that ever formed. It's a different picture of how the early universe grew, and one that some physicists take seriously. Others go even further and question the entire framework of dark matter. In models like MOND, the need for dark matter disappears, and the missing satellites problem may not exist at all. But these alternative models come with trade-offs. While they may help with one issue, they often struggle to match the full range of cosmic observations. As a result, most astronomers still lean toward dark matter being real but complex, and the missing satellites problem as something that needs refinement, not a full rewrite. The Vera C. Rubin Observatory, which is nearly set to begin full operations, will scan the entire southern sky in great detail and will find dozens or even hundreds of new faint dwarf galaxies, many of which could be orbiting the Milky Way or nearby systems like Andromeda. That might help close the gap between prediction and observation, or open up new puzzles. Some are turning to simulations that include more realistic physics. Older simulations focused mostly on gravity and dark matter. Newer ones include the effects of gas, radiation, and star formation. These hydrodynamical simulations show that feedback from stars, winds, supernovae, and radiation can blow gas out of small galaxies, slowing or stopping star formation. That means many halos might have started to build galaxies, only to be shut down early. These effects could naturally explain why some dark matter halos remain dark. Some small galaxies might be hiding in plain sight, having been stretched and distorted by interactions with the Milky Way. These are known as tidal streams, long trails of stars pulled out of dwarf galaxies as they get too close to our galaxy. Instead of appearing as compact objects, these galaxies are shredded into faint arcs. Detecting and identifying these streams takes careful work, but more are being found every year. So far, there's no single explanation that solves the missing satellites problem completely. It may take a combination of answers, and our models may still be missing key pieces of the story. This problem touches many parts of cosmology. It affects how we understand dark matter, galaxy formation, and even the conditions of the early universe. And while the largest structures in the cosmos get much of the attention, the smallest ones that might also hold some of the biggest clues. Antimatter deficiency. Why is the universe so biased? After the Big Bang, the universe was supposed to have produced equal amounts of matter and antimatter. Both matter and antimatter are made up of similar particles, but with opposite properties. For every particle of matter, there's a corresponding antiparticle of antimatter. In theory, when matter and antimatter meet, they annihilate each other, releasing energy in the process. So, with the universe being born from this intense energetic event, it was expected that matter and antimatter would have balanced each other out. The result? A universe filled with nothing but radiation, with no atoms, stars, planets, or life. But that's not what happened. Instead, the universe today is made almost entirely of matter. There's a very small amount of antimatter around, but it's largely absent in the cosmos. Why is the universe so biased toward matter? Why did it seem as though, when matter and antimatter were created, one somehow came to dominate the other, leaving a universe where everything we see, galaxies, stars, planets, and even ourselves, is made up of matter, and almost no antimatter is left? This imbalance between matter and antimatter is known as the baryon asymmetry problem. When we look out into the universe, we see no large concentrations of antimatter. If there were significant amounts of antimatter out there, it would interact with matter, creating gamma rays and other detectable signals. Yet, scientists haven't found any large pockets of antimatter, at least not in the quantities that would be expected if the Big Bang really did create equal amounts of matter and antimatter. The Big Bang, in theory, created a perfect symmetry between matter and antimatter. But today, even the small amounts that we do see are isolated to special locations, such as in cosmic rays, where antimatter particles are sometimes detected as they travel toward Earth. These particles, though, are rare, and they don't add up to the mass of matter we observe in the universe. As the universe expanded and cooled, the energy from the Big Bang started to form particles. First, light ones like electrons and positrons, the antimatter counterpart to the electron. These particles quickly met and annihilated each other, producing more energy in the process until the universe cooled to the point where particles could form stable structures. At some point during this process, the balance between matter and antimatter was broken. Something happened that caused just a tiny bit more matter to survive than antimatter. And once the antimatter had annihilated the vast majority of the antimatter particles, there was a slight excess of matter left over. This tiny surplus of matter is what became the atoms, stars, galaxies, and everything that makes up the visible universe today. If this imbalance hadn't occurred, then we would be left with nothing but radiation. What caused this unbalanced outcome, which laid the foundation for the universe we know and live in? Scientists have proposed several theories. These explanations often involve mechanisms that could have tipped the scales, just enough to create the surplus of matter we see today. One of the most important ideas is CP violation, a phenomenon in which the symmetry between matter and antimatter is broken. CP violation refers to the idea that the laws of physics behave differently for particles and their antiparticles, not just when they are swapped, aka C-symmetry, but also when their motion is reversed, aka P-symmetry. In simpler terms, the laws of physics may favor the behavior of matter over antimatter under certain conditions, allowing matter to survive and antimatter to be annihilated. This kind of violation has been observed in certain types of particle interactions, specifically in the decay of certain types of particles called kaons and B-mesons. These particles are unstable and decay into lighter particles, but the rate of their decay differs slightly when the particles are matter versus antimatter. This small imbalance over time could have led to a slight excess of matter over antimatter in the early universe. However, while CP violation in these processes has been observed in laboratory experiments, it's not enough to explain the large imbalance between matter and antimatter we see today. In order to fully account for the matter-dominated universe, additional factors are likely at play. One possibility is that there were non-equilibrium conditions in the very early universe, conditions that allowed for more matter to survive than antimatter. If the universe expanded rapidly enough in its infancy, it could have created conditions where the production of particles didn't perfectly follow the symmetry we would expect from a simple Big Bang model. Perhaps particles beyond those that we currently know about were created in the early universe and played a crucial role in tipping the balance. Some researchers have suggested that these particles could interact with matter and antimatter, possibly favoring matter over antimatter in ways that are undetectable with current technology. Another possibility is that the universe's apparent bias toward matter could be a consequence of physics on scales beyond our current understanding, possibly related to quantum gravity, the theory that attempts to merge general relativity with quantum mechanics, which describes the behavior of particles on the smallest scales. If gravity itself interacts with matter and antimatter in a unique way, this could help explain the disappearance of antimatter from the observable universe. The issue of antimatter deficiency also has profound implications for the search for life beyond Earth. For many years, scientists have used the idea that intelligent alien civilizations might use antimatter as a fuel source. If there were large quantities of antimatter in the universe, they might be detectable, either in cosmic rays or in potential energy sources like antimatter-powered spacecraft. Yet, the scarcity of antimatter in the cosmos means that we are left to look for other signatures of alien life, perhaps in the form of signals or technological artifacts, rather than expecting to find large quantities of antimatter itself. The faint young sun. Paradox: why was early Earth not a snowball? When we think about the early history of our planet, the image that often comes to mind is one of a hot and volatile surface, with volcanic eruptions spewing gases into the atmosphere and a lack of stable conditions for life. However, this early Earth wasn't as inhospitable as it might sound, and it had something that should have been impossible: liquid water. This raises a major question for scientists. How did Earth manage to stay warm enough to support liquid water when the Sun, billions of years ago, was much dimmer than it is today. This puzzle is known as the faint young sun paradox. The sun we see today is far brighter than it was when it first formed. The sun started out as a young star around 4.6 billion years ago, and in its early years, it emitted only about 70% of the energy it radiates now. Despite this, Earth's surface temperature was warm enough to keep water in liquid form. So how did the planet avoid freezing over and developing into a frozen snowball Earth? The traditional theory for sustaining a warm planet in the distant past has always been the role of greenhouse gases. On Earth, these gases, such as carbon dioxide and methane, trap heat in the atmosphere, preventing it from escaping into space. In modern times, these gases keep our planet warm enough to sustain life. The assumption is that in the past, Earth's atmosphere would have contained much higher levels of these gases, allowing more heat to be trapped, even with a weaker sun. This warming effect, called the greenhouse effect, would have helped to offset the sun's faintness, keeping the planet warm enough for liquid water. However, the early Earth was thought to have a similar level of carbon dioxide as we have today, and though this would have helped trap some heat, it's still not clear how it could have been enough to keep the planet from entering a snowball state, where the planet would be completely frozen, with ice sheets extending to the equator. In other words, even with higher levels of greenhouse gases, there still doesn't seem to be enough warmth generated to explain Earth's conditions at the time. One possible explanation lies in a more complex interaction between the Earth's atmosphere, oceans, and the greenhouse gases present. There is evidence to suggest that early Earth may have had higher concentrations of greenhouse gases, and in particular, there may have been much larger amounts of methane, a potent greenhouse gas that is much more effective at trapping heat than carbon dioxide. In combination with carbon dioxide, methane could have created a powerful warming effect that kept Earth's surface temperature above freezing. However, methane would have been rapidly broken down by the sun's ultraviolet radiation, which raises the question of how it could have persisted in the atmosphere long enough to play a significant role. One possibility is that the methane was continually replenished through volcanic activity and other geological processes. The early Earth was an active place, with volcanoes spewing gases like methane and carbon dioxide into the atmosphere. If this volcanic activity was frequent and widespread, it could have produced enough greenhouse gases to maintain a warm climate. This idea fits well with evidence that suggests early Earth had a much higher concentration of volcanic activity than it does today. Another possible factor could have been the planet's albedo, or its ability to reflect sunlight. In the early days of Earth, the planet was likely covered with thick clouds of water vapor and other particles, which could have acted to trap more heat, further warming the planet. Clouds are excellent at reflecting sunlight and keeping heat close to the Earth's surface. The presence of such clouds could have created a kind of blanket that prevented the sun's energy from escaping. Moreover, the oceans themselves may have played a crucial role. Water has a much higher heat capacity than air, meaning it can store heat much more efficiently. The early Earth likely had large, shallow oceans that could absorb heat from the sun and slowly release it over time. This would have helped to maintain a relatively stable temperature, preventing sudden drops in temperature that could have led to freezing. These oceans would have been able to act as a heat reservoir, absorbing energy from the sun and preventing drastic temperature fluctuations that would have made it impossible for life to exist. Even with these explanations, scientists still don't have a full picture of how the Earth avoided a snowball state. There may be factors that we are still not fully aware of, factors that played a role in stabilizing Earth's climate in ways that we cannot easily detect from the evidence available today. New models and simulations of the early Earth's climate are continually being developed, and some researchers even suggest that there might have been a different kind of atmospheric chemistry at work in the early days of our planet, something that is not immediately apparent in the geological record. In recent years, some have proposed an alternative theory that suggests the Sun may have been even dimmer. The weak sun theory holds that the sun's early output of light and heat was lower than the 70% estimate, which could further complicate efforts to understand the paradox. If the early sun were dimmer, the greenhouse gases in Earth's atmosphere would have had to work even harder to keep the planet warm enough for liquid water. Yet another possibility is that the early Earth wasn't entirely as hospitable as we imagine. It could have been a planet marked by extreme volatility with frequent ice ages and periods of heat. These fluctuations in temperature would have been rapid and extreme, but still allowed pockets of liquid water to exist, potentially allowing life to begin and evolve in isolated niches. There's much that we don't know about the conditions that allowed life to begin, and the interplay of different factors, volcanic activity, atmospheric chemistry, the sun's changing luminosity, and the role of Earth's oceans and climate could be more complicated than we imagine. Despite decades of research and numerous theories, the paradox remains unsolved, urging scientists to continue exploring the Earth's early history. As we learn more about other planets, particularly outside our own solar system, we may one day find clues that help answer this age-old puzzle. Anomalous microwave emission from the Milky Way, spinning dust or something else. While mapping the Milky Way's microwave emission, researchers noticed a strange kind of glow scattered across the galaxy. It wasn't coming from stars or gas or anything familiar. It was faint, but consistent. This glow didn't match known sources of microwave radiation, and it seemed to trace the dusty regions of the galaxy, especially where star formation was happening. It came to be known as anomalous microwave emission, or AME. The glow appeared in multiple surveys and showed up across different telescopes. It didn't match the CMB, and it also didn't look like synchrotron radiation, which is made when charged particles spiral through magnetic fields. Nor did it match thermal emission from regular dust grains, which glow at longer wavelengths. As scientists dug deeper, one explanation began to rise to the surface: spinning dust. It was a strange idea at first, but it started to make sense. The galaxy is full of tiny dust grains. Some are just big enough to reflect visible light, while others are so small they're more like molecules. These smallest grains, some just a few nanometers across, can spin incredibly fast. And if they carry a tiny electric charge, their rotation could create electromagnetic radiation. If enough of these spinning dust grains are scattered through the galaxy, they could give off the microwave glow seen in AME. This idea fit the data better than anything else, at least for a while. The brightest AME regions seemed to line up with where these very small dust grains, often made of complex molecules like polycyclic aromatic hydrocarbons, or PAHs, were expected to be. These molecules form in the shells around dying stars and spread into the galaxy. They're excited by ultraviolet light from young stars, which makes them spin faster. It made sense that this could be the source of the odd microwave light, but the exact shape of the microwave signal varied. In some regions, the glow peaked at slightly different frequencies than in others. In some clouds, the signal was stronger than expected, and in others, it was weaker. If it was all just spinning dust, why wasn't the pattern more uniform? The small differences hinted that something more complicated might be going on, or that another source of radiation could be mixed in. Moreover, there were a few places where AME seemed to show up without the expected presence of dust grains. In some star-forming regions, where scientists expected to find PAHs lighting up, there wasn't as much of the expected mid-infrared signal that usually goes with these particles. And in other regions, the AME was unusually strong. So far, no one has found a better explanation that fits all the data. Spinning dust remains the leading idea, but not the only one. Some researchers have suggested that magnetic grains, tiny pieces of iron or similar materials, could also spin and radiate microwaves. These would be harder to detect in other wavelengths, so they might contribute to the signal without showing up clearly elsewhere. Others have explored whether strange quantum effects in the cold interstellar medium might play a role, although these ideas are harder to test directly. Another line of thinking looks at how the particles interact with the surrounding gas and radiation. If the spinning grains are affected by electric fields, collisions, or even changes in local temperature, that could shift their microwave emissions slightly. These effects might explain the variations from region to region, but modeling all these small-scale processes is difficult. It involves complex physics, and even small differences in the grain size, charge, or environment can change the final result. What makes this mystery so important is that AME shows up in places where scientists are trying to study the early universe. Missions like WMAP and Planck were designed for the CMB, but the Milky Way's own emission gets in the way. To get a clear view of the early universe, scientists have to remove all the foreground signals, including AME. If the nature of this microwave glow isn't fully understood, it could affect the accuracy of those maps. In recent years, efforts have been made to map AME more carefully, to track where it appears and how it behaves. These studies use data from multiple telescopes at many different wavelengths to cross-check the signal and build a clearer picture. Some ground-based radio observatories have joined the effort, as have newer infrared and microwave instruments on satellites. Perhaps the AME might be telling us something deeper about the interstellar medium. This region, though it looks empty, is filled with gas, dust, magnetic fields, and high-energy particles. It's a dynamic, constantly changing environment shaped by supernova blasts, starlight, and galactic winds. The tiniest particles in this space can interact in surprising ways. AME could be one of the first clear signals from these tiny interactions, a kind of glow from the hidden physics of the galaxy's background material. Even in the age of high-resolution maps and supercomputers, the galaxy still holds surprises. The AME produces signals that defy easy explanation. And often, the strangest discoveries are the ones that come from looking between the known sources, from watching the background and finding that the background itself is full of mystery. The curious silence of the hydrogen line. In the early days of the search for life beyond Earth, scientists looked to the stars, not just with telescopes, but with radios. The idea was simple. If we were trying to reach another civilization far away, using radio would make the most sense. It's cheap, it travels fast, and it moves through space without being blocked by clouds, dust, or most of the things that get in the way of light. Among the many frequencies that radio waves can take, one stood out. A frequency of 1420.40575 MHz. Known as the hydrogen line, it is the frequency emitted by neutral hydrogen atoms when their lone electron flips its spin. It's a quiet, natural signal, and it's found all over the galaxy. That made it a perfect place to listen. In fact, many astronomers and thinkers believed that if another intelligent species existed, and if they were trying to communicate, they would use that exact frequency. It's easy to find, it's easy to detect, and it's a kind of universal standard. Hydrogen is the most abundant element in the universe, and its signal, they thought, would be something that any advanced species would know to use. This belief became a foundation of SETI, the search for extraterrestrial intelligence. For decades, scientists have pointed their radio telescopes at the sky, tuning them carefully to the hydrogen line. They've scanned stars, galaxies, and parts of the sky that seem quiet, hoping that maybe, just maybe, there would be something unusual. A narrow band signal, a whisper in the static that wasn't caused by nature, but that signal has never come. Despite years of watching and waiting, there's only been silence. Not even a blip that we can confirm. And this has puzzled scientists. The hydrogen line makes too much sense. It sits in a quiet part of the radio spectrum, away from most natural background noise. And yet, it remains quiet. The universe, at 1420 MHz, has given us nothing unexpected. Were we wrong to expect that others would use this frequency? Could it be that intelligent life doesn't communicate the way we thought? Or are we missing the signals entirely? There are many possible explanations. One is that intelligent life is simply rare. Maybe we are the only ones broadcasting or listening at this moment in time. The universe is vast, and even with thousands of galaxies and trillions of stars, intelligent civilizations could be few and far between. If their signals are weak or distant, even the best telescopes on Earth may not be able to detect them. Another idea is that civilizations don't use radio at all, or at least not anymore. Radio might be just a brief phase, like smoke signals or Morse code. Advanced civilizations may have moved on to better technologies. They might use lasers, quantum signals, or communication systems we haven't even dreamed of yet. If that's the case, then tuning into the hydrogen line would be like listening for telegrams in a world of fiber optics. There's also the chance that signals are out there, but we're not looking the right way. Radio telescopes have a narrow field of view. They can only scan a small part of the sky at a time, and the universe is big. A signal could flash by when no one's watching, or it could come in a form we don't recognize. If it's not steady or doesn't repeat, it might be dismissed as noise or interference. We could be getting signals and just not realizing it. Interference from Earth is also a major problem. The 1420 MHz band is protected for astronomy, but that doesn't stop nearby devices or distant satellites from leaking into the range. Cars, phones, aircraft, and even microwave ovens can sometimes create static that masks real cosmic signals. Sorting out Earth-based noise from real cosmic transmissions is one of the biggest challenges in radio astronomy. A weak alien signal buried in this mess could easily be missed. Some researchers have even suggested that intelligent civilizations might avoid the hydrogen line on purpose. If every other civilization is also listening at that frequency, it could become crowded or noisy. Others may think the same way and deliberately choose a different band to communicate, or maybe they're afraid to broadcast at all. The idea of radio silence has been proposed in some science circles. The idea that smart civilizations might avoid sending signals to avoid detection. If the universe has dangers we don't know of, staying quiet might be the safest choice. Still, the hydrogen line's importance goes beyond just being a convenient frequency. It represents a kind of natural language, a baseline for the universe. In fact, one of the earliest attempts to send a message to space, the 1974 Arecibo message, was broadcast near the hydrogen line. It used binary codes, arranged in a way that described the basics of human life, our DNA, and the shape of our solar system. Some have suggested that advanced species might encode messages into the natural hydrogen line itself. Because the frequency is always there, perhaps someone has found a way to subtly modify it. They might be sending information hidden in the timing or structure of hydrogen emissions, changes so slight that we haven't noticed them yet. Though no evidence of such encoding has ever been found, it shows just how many angles scientists are exploring. Others are turning to new methods of listening. Instead of focusing just on narrow bands like the hydrogen line, newer SETI projects are casting wider nets, using machine learning to search vast parts of the spectrum all at once. Some projects are even using distributed computing, where volunteers across the globe help analyze the data from radio telescopes in their spare time. These modern tools may help us catch things we've missed. But still, the original mystery remains. Why is one of the quietest, clearest frequencies in the universe still so empty? The hydrogen line silence doesn't mean we're alone. It just means that the universe isn't as simple or predictable as we once hoped. Maybe others don't think like we do. Maybe they're not trying to reach out at all, or maybe they did, and the signals are already on their way, just too far to have arrived yet. For now, the hydrogen line hums quietly in the background of space, the steady whisper of neutral hydrogen atoms doing what they've done since the universe began. Diffuse interstellar bands, a century-old spectral enigma. In the early part of the 20th century, astronomers were refining the use of spectroscopy to study the stars. When the light from stars passed through their instruments, they expected to see a pattern of lines. These lines, some bright, some dark, were like fingerprints. They came from atoms and molecules in the stars themselves, or from materials in space between the stars. Each element left its own mark, and scientists could use those marks to learn what stars were made of, or how fast they were moving. But in many cases, there were dark lines that didn't make sense. They didn't match any known atoms. They didn't follow the same patterns seen from gases like hydrogen or helium. These lines were often wide and faint, unlike the sharp lines seen from individual elements. And they didn't seem to come from the stars. Instead, they appeared to be imprinted on the light as it traveled through space. These strange features came to be known as diffuse interstellar bands, DIBs for short. At first, some scientists thought these lines were just flaws in the equipment or mistakes in how the data was read. But over time, it became clear that the bands were real. They showed up in the light from many stars, and they always seemed to appear when the starlight passed through clouds of interstellar dust or gas. That meant whatever was causing them wasn't near the star. It was somewhere in the space between the stars. By the 1930s, astronomers had catalogued dozens of these bands. Over the decades, the number kept growing. Today, scientists have recorded over 500 distinct DIBs. They appear all across the visible spectrum and even into the infrared and ultraviolet. They vary in width, strength, and shape. Some are found in nearly every line of sight through the Milky Way. Others are more rare or appear only under specific conditions. The mystery is that no one knows exactly what causes them. For over a century, scientists have been trying to match the DIBs with known molecules. They've tested gases in laboratories, shining light through them to see what kinds of absorption lines they create. They've tried to recreate the cold, thin conditions of deep space to simulate what might be happening in the interstellar medium. And yet, for most of the DIBs, there are no matches. Some of the most likely candidates are large carbon-based molecules. These include things like PAHs, fullerenes like the famous buckyballs, and long carbon chains. These molecules can survive in space and are known to absorb light. They can also be quite stable, even under ultraviolet radiation. But while they seem to be good suspects, confirming them is another story. The problem is that these molecules are hard to study in the lab. They are complex, fragile, and difficult to produce in the exact conditions found in space. Their spectra can change depending on their temperature, their charge, or even how they twist and vibrate. Matching a DIB to a molecule isn't just about lining up one dark line in the spectrum. It's about matching many lines across different environments and proving that the molecule really behaves the same way in space. So far, only a handful of DIBs have been matched with high confidence. One major breakthrough came in 2015, when researchers identified two specific DIBs that seemed to match the spectra of ionized C60 molecules. This was a big step forward. It showed that at least some DIBs are caused by real molecules that we can study. Space is full of complex chemistry. Clouds of gas and dust contain organic compounds, radicals, and charged particles. Some of these molecules might exist only for short periods of time. It's possible that the DIBs come not from one source, but from a mix of many different things, each contributing to different bands. Even if we don't know what causes them, we can still use them to learn about space. Their strength and shape can tell us how much material the starlight has passed through. Some bands are stronger in regions with more dust, while others seem to trace specific types of interstellar clouds. By studying DIBs, astronomers can map the structure of our galaxy, measure the composition of the interstellar medium, and trace the history of gas flows between stars. In recent years, astronomers have also begun studying DIBs in other galaxies. Using large telescopes and powerful spectrographs, they've detected these bands in the light from galaxies millions of light-years away. That shows that whatever causes DIBs isn't just a feature of our own Milky Way. It's a part of the wider universe. The same unknown molecules or processes are present in galaxies far beyond our own. Space-based observatories avoid the interference of Earth's atmosphere and are providing clearer views. Advanced computer models are also helping researchers simulate the behavior of complex molecules under different conditions. Still, the pace is slow, and after more than 100 years, DIBs remain one of the longest-running puzzles in astronomy. The bands are etched into the light of stars, but they don't give up their secrets easily. Even something as simple as a dark line in a spectrum can resist explanation. The answers may be just around the corner, or they may take another 100 years to uncover. In the meantime, astronomers continue to watch, to listen, and to wonder. Unexplained gamma-ray bubbles above and below the Milky Way. In 2010, scientists working with NASA's Fermi Gamma-Ray Space Telescope found two enormous shapes stretching above and below the center of the Milky Way. Each one extended roughly 25,000 light-years, creating a pair of bubble-like structures reaching far into the galaxy's halo. The discovery was sudden, surprising, and difficult to explain. These structures were quickly named the Fermi bubbles. They are filled with gamma rays, the most energetic form of light. These rays are invisible to the human eye, but can be detected by space telescopes like Fermi. At first glance, the bubbles seemed to appear out of nowhere. They were not seen in earlier data simply because scientists weren't looking for them in quite the right way. But once they were noticed, it became clear how massive and sharp-edged they were. They seemed to be a major feature of the Milky Way, hiding in plain sight. The Fermi bubbles raised a lot of questions right away. What caused them? Why do they glow in gamma rays? And how old are they? One theory points to the supermassive black hole at the center of the Milky Way, known as Sagittarius A star. Like all galaxies, the Milky Way has a huge black hole at its core, millions of times more massive than the Sun. Normally it's quiet, only gently pulling in gas and dust. But sometimes, black holes go through active periods. They consume large amounts of material, which heats up and sends out powerful jets or winds. This activity can create massive outflows that shoot high-energy particles far into space. If Sagittarius A star had a burst of activity several million years ago, it might have created the Fermi bubbles. The black hole could have swallowed a sudden inflow of gas, releasing a huge amount of energy in the process. That energy would have blasted material outward, possibly forming the twin bubbles. Over time, this material would collide with other gas and particles in space, creating shock waves and glowing in gamma rays. Another possibility is that the bubbles were caused not by the black hole, but by a wave of star formation in the center of the galaxy. In this scenario, massive stars formed rapidly in the past, lived short, violent lives, and then exploded. Those explosions released huge amounts of energy, and together they could have pushed gas outward from the galactic center, forming the bubbles. Both ideas could have supplied the energy needed to carve out such large and symmetrical structures, but there's no clear evidence to say for certain which one it was, or even if it might be a mix of both. Scientists have continued studying the bubbles using not just gamma-ray observations, but data from other wavelengths as well. X-ray telescopes, microwave detectors, and radio observatories have all contributed pieces to the puzzle. One of the more interesting findings came from observations made by the Planck satellite, which detected something called the microwave haze. This haze overlaps with the bubbles, suggesting that electrons moving through magnetic fields might also be involved in creating the glow. There's also evidence from X-rays that points to hot gas being present within the bubbles. This gas may be moving outward at hundreds or even thousands of kilometers per second. That tells researchers that the event or process that formed the bubbles wasn't just energetic. It had enough force to heat and move matter across vast distances. Still, the exact mechanism remains unclear. One complication is that the edges of the bubbles are sharply defined. If the bubbles were very old, you might expect their edges to blur over time. The fact that the bubbles remain so distinct suggests that they might be relatively young, perhaps only a few million years old. That's a short time on galactic scales. There are galaxies where black holes are active and create similar outflows. Some of these galaxies have visible jets or lobes that stretch out into space, glowing in various forms of radiation. But the Milky Way isn't one of those galaxies. Its central black hole seems quiet by comparison. If Sagittarius A star did create the bubbles, then it must have gone through a rare and short-lived active period. That would make this a unique window into our galaxy's past. Another open question is what exactly is producing the gamma rays? High-energy light can come from many different sources. One likely explanation is inverse Compton scattering. In this process, electrons moving at near-light speeds collide with lower-energy photons, like those from starlight or the CMB, and give them a boost. These photons then jump into the gamma-ray part of the spectrum. That would explain the glow without needing the bubbles themselves to be radioactive or especially hot. But again, this depends on the details. Where did the electrons come from? How fast are they moving? How long can they remain trapped inside the bubbles before escaping? Some models suggest that magnetic fields might help keep the particles contained, allowing them to continue interacting with photons over long periods. Other models argue that fresh particles must be injected into the bubbles regularly, possibly from ongoing activity in the galactic center. The bubbles are almost perfectly aligned above and below the galactic plane. That kind of balance is hard to produce by accident. Whatever caused them must have acted along a well-defined axis centered on the core of the galaxy. That again points to either a focused outflow from the black hole or a structured burst of star formation that was confined to the central region. As more data has been collected, researchers have also begun looking at smaller structures related to the bubbles. In some observations, fine ripples or filaments have been seen inside the bubbles, as if the gas inside is still moving or interacting with surrounding materials. These features may help reveal the history of the bubbles, whether they were created in a single blast or in waves over time. If the galaxy's center was once more active, what caused it to quiet down? Could it become active again in the future? Do the bubbles play a role in how gas flows in and out of the galaxy, affecting star formation and galactic evolution? There are no firm answers yet. The more researchers study the bubbles, the more possibilities they find. Some even suggest that the Fermi bubbles could connect to other unexplained features in the galaxy, like strange microwave or X-ray signals. They might be part of a bigger system of outflows, winds and particle interactions that we still don't fully understand. The 3.5 keV line, possible signal from decaying dark matter. In 2014, a group of astronomers were looking at clusters of galaxies using telescopes like XMM Newton and Chandra, which can see high-energy light that human eyes can't detect. Buried in the data, at a very specific point in the spectrum, 3.5 keV, they saw a faint but curious signal. It was a tiny extra bump in the light, but it stood out just enough to make scientists stop and ask what it could be. At first, it looked like just another part of the data. Space is full of X-rays. They come from hot gas, exploding stars, and black holes swallowing matter. Most of these X-rays make up a smooth background, but the 3.5 keV line didn't match any known source. It wasn't tied to iron or oxygen, or any of the other usual suspects. And because the signal showed up not in just one place, but in several galaxy clusters, it hinted at something that might be happening across the universe. That's when people started to wonder if this tiny signal could be something much bigger, maybe even a clue about dark matter. One theory about dark matter is that it could be made up of particles that decay over time. That means they slowly fall apart, releasing energy as they do. If one of these particles were to decay into a lighter particle and a photon, it might release a tiny flash of light, possibly an X-ray. And if a dark matter particle released a photon with 3.5 keV of energy, it would show up exactly where the mysterious signal was found. The idea caught on quickly. Scientists started to look for the 3.5 keV signal in more places. They examined data from the Perseus cluster, one of the brightest X-ray sources in the sky. They studied the Andromeda galaxy. They even looked at our own Milky Way. And in some of those places, the signal seemed to be there again, always faint, but present. This led to a wave of excitement in the scientific community. Maybe, just maybe, we were seeing dark matter decay for the first time. If true, it would be one of the biggest breakthroughs in physics. It would help explain a mystery that has lasted for decades. It would also point to a specific kind of dark matter particle, something like a sterile neutrino, an invisible cousin of the regular neutrino, but one that might decay in just the right way. But as more people looked, the picture got murkier. Not every observation showed the signal. Some telescopes couldn't find it at all. Others saw hints, but not enough to say for sure. The line didn't always appear as clearly or in the same strength. In some cases, it seemed stronger in one galaxy cluster and weaker in another. That didn't match the way dark matter should behave if it were truly universal. Some scientists began to question whether the signal was real at all. X-ray telescopes are very sensitive, but they're also complicated. Small errors in calibration or background noise can create fake signals. One team suggested that the 3.5 keV line could be caused by potassium or chlorine atoms in hot gas, whose emission lines hadn't been accounted for properly. Others said it could be an artifact of how the data was processed. The debate grew more intense as new instruments got involved. Japan's Hitomi satellite, launched in 2016, was designed to measure X-rays with higher precision than any previous telescope. Scientists hoped it could confirm the 3.5 keV line once and for all. But just over a month after launch, Hitomi malfunctioned and broke apart in orbit. Before the accident, it had managed to collect some data from the Perseus cluster. When scientists analyzed that small amount of data, they didn't find the signal. That was a big blow to the dark matter theory. Even so, the mystery didn't die. Some teams returned to earlier data, rechecking and reanalyzing it using better techniques. Others proposed that the dark matter explanation might still work, but only under special conditions. Maybe the signal is only visible in certain types of galaxies, or only when dark matter is especially dense. Maybe the decay is rare and only noticeable in specific environments. Or maybe the particle doesn't decay directly into a photon, but goes through several steps first. If the 3.5 keV signal comes from decaying dark matter, the signal should be strongest in places with the most dark matter, like the centers of galaxies and clusters. But in some studies, the line didn't seem to follow that pattern. It appeared more in the outskirts or was oddly uniform. That doesn't make much sense if the source is tied to dark matter alone. Some scientists accepted the signal as real, but looked for other explanations. Maybe it's not dark matter at all. Maybe it's due to some unknown process in hot plasma or a strange behavior in how certain atoms emit light under extreme conditions. Others suggested it might be caused by axions, which could create a 3.5 keV line without needing dark matter to decay at all. The fact that the signal has stayed so faint and hard to pin down only makes it more intriguing. The European Athena X-ray Observatory, planned for launch in the 2030 S, will offer much better sensitivity and resolution. It may finally settle the debate. Until then, researchers continue to dig into old data, searching for patterns, errors, or new signals that could help make sense of the 3.5 keV line. The p-nuclei puzzle. How are these rare isotopes made? The periodic table tells the story of how matter builds itself in the universe. From the simplest element, hydrogen, to the heavier ones like iron and gold, we now understand much about where these elements come from. Some elements form in slower processes, like in aging stars, while others form quickly in violent events, like neutron star collisions. But there's a group of isotopes, known as the p-nuclei, that don't quite fit into any of the usual patterns. They're rare, hard to explain, and scientists don't fully understand where they come from. The P in p-nuclei stands for proton-rich. These are specific isotopes of various elements that have more protons and fewer neutrons than normal. They are stable, meaning they don't fall apart, but they're not easy to make in the usual kinds of nuclear reactions. There are about 35 of these proton-rich isotopes scattered across the periodic table. Some of them include isotopes of molybdenum, ruthenium, and samarium. They're found on Earth in very small amounts, and scientists have also seen their signatures in stardust and meteorites. but how the universe creates them is still a mystery. They don't come from the two main types of nuclear reactions that build heavy elements. One of those is called the S process, or slow neutron capture. It happens in older stars, where atoms slowly collect neutrons and gradually build up to heavier elements. The other is the R process, or rapid neutron capture, which takes place in extreme environments like supernova or neutron star mergers. Both these methods add neutrons to atomic nuclei. But the P nuclei have fewer neutrons, not more. That means they can't be made by simply stacking more neutrons onto lighter elements. One idea for P nuclei creation is that they are formed when existing nuclei are hit by high-energy photons which can knock neutrons out of the nucleus. This is known as the gamma process. It could happen in very hot parts of exploding stars, where the temperatures are high enough to strip away neutrons. If a nucleus loses enough neutrons in this way, it could turn into one of the rare proton-rich isotopes. But when researchers try to model the gamma process using computers, they often find that it can't produce enough of the lighter P nuclei, especially isotopes like those of molybdenum and ruthenium. The gamma process seems to work better for the heavier isotopes, but it struggles to explain the lighter ones. That suggests there's either something missing in the models or that another process must be involved. One alternative idea is the neutrino process. In this scenario, during a supernova explosion, a burst of neutrinos, tiny particles that barely interact with matter, might hit atomic nuclei and change their structure. These neutrino interactions could lead to the creation of some P nuclei, especially the lighter ones. But the conditions for this to happen are very specific, and the number of neutrinos needed would have to be just right. Another proposal is the RP process, or rapid proton capture. This would involve protons being added quickly to atomic nuclei in a high-temperature environment, such as on the surface of a neutron star. If the environment has a lot of hydrogen and extreme pressure, the nuclei could grab protons before they decay. This kind of process might produce some of the P nuclei. We've never directly observed the RPP process in action, and the conditions for it to happen are difficult to confirm. There's also the PN process, which is a more recent suggestion. In this idea, protons and neutrons are both added to a nucleus at the same time, which might happen in explosive events that are rich in both types of particles. This process could help explain certain isotopes that don't quite match the other models. But like the others, it's still being studied and tested. The trouble with all these theories is that they rely on environments that are hard to observe directly. We can't watch the inside of a supernova in real time. We can only see the light and particles that come out of it. That means much of our understanding of nucleosynthesis, the creation of elements, comes from simulations, lab experiments, and the study of ancient stardust. In the case of the P nuclei, even those tools are limited. Researchers have tried to study the P nuclei by looking at meteorites. These space rocks often contain grains of material that formed before the solar system existed. Inside those grains, scientists can sometimes find clues about the types of nuclear reactions that occurred in the stars that created them. Some grains show isotopic ratios that hint at P nuclei formation, but the samples are small and the data is difficult to interpret. Laboratories on Earth have also tried to create the P nuclei by smashing particles together in accelerators. These experiments can help measure reaction rates and cross-sections, which are important for understanding how certain isotopes form. But even with today's best equipment, it's hard to recreate the exact conditions of a supernova or neutron star surface. The temperatures and pressures involved are beyond anything we can produce on Earth. One of the most important efforts to solve the P nuclei puzzle involves combining observations with nuclear physics models. Astronomers are working with particle physicists to refine the models that describe how nuclei behave under extreme conditions. They are trying to measure reaction rates more precisely and to understand how different processes might work together. Instead of relying on a single process to explain everything, scientists are now considering that the P nuclei may come from a mix of environments. some from the gamma process, others from neutrino-driven reactions, or even rare kinds of stellar collisions. The rarity of the P nuclei makes the search pretty challenging. They make up only a tiny fraction of the heavy elements in the universe. That means even small errors in the models can have a big effect on the predicted amounts. And because they're so rare, detecting them in space or in laboratory samples is a slow and careful task. For now, the P nuclei sit in the background of our world, in tiny amounts in the Earth, in grains of meteorites, in the light from dying stars. They are part of the story of matter, but their part is still not fully written. The solar cycle's predictability problem. The Sun is a dynamic and ever-changing force. It experiences regular cycles of activity that influence everything from solar wind to the auroras we see at the poles, even impacting the technology we rely on here on Earth. These cycles are known as the solar cycle, and they span roughly 11 years, with the Sun moving between periods of high and low activity. During these periods, solar flares, sunspots, and coronal mass ejections, or CMEs, vary in number, and these fluctuations can have both fascinating and potentially harmful effects on Earth. However, despite decades of research, predicting the timing and intensity of these solar cycles remains an inexact science. The problem is not just that the Sun behaves unpredictably, it's that we can't seem to pinpoint exactly what drives these changes. We know the solar cycle is closely tied to the Sun's magnetic field, but exactly how and why this magnetic activity evolves the way it does over time is still shrouded in mystery. For scientists, predicting the solar cycle involves observing patterns in the Sun's activity, measuring sunspots, and tracking the magnetic fields that drive the solar wind. But it's still a challenge to accurately forecast the cycle's strength or its exact timing. The Sun's activity, which we call the solar cycle, can be thought of like a heartbeat. It rises and falls with regularity, each cycle beginning with a period of minimal activity, often called the solar minimum, and building up to a peak of intense solar activity, known as the solar maximum. During the solar maximum, the Sun is most active, with numerous sunspots, solar flares, and CMEs. Sunspots are dark areas on the Sun's surface where the magnetic fields are most concentrated and are often considered the most visible sign of the solar cycle. These spots appear and disappear over time, and their number is directly linked to the Sun's magnetic activity. At the peak of the solar cycle, sunspots reach their highest numbers, often going hand in hand with a spike in solar flares, intense bursts of radiation that can travel through space, affecting satellites and power grids on Earth. CMEs, which are massive bursts of solar wind and magnetic fields rising above the solar corona, can also have devastating effects on technology, as these energetic bursts interact with Earth's magnetic field, causing geomagnetic storms. These storms can knock out satellite communications, disrupt GPS systems, and even cause power grid failures, showing just how much the Sun's activity can impact our daily lives. The transition between solar minimum and solar maximum is what defines the solar cycle, but predicting when the next peak will arrive and how intense it will be is a puzzle. Solar cycles are not identical, and sometimes the intensity and frequency of sunspots can vary dramatically from one cycle to the next. A solar cycle might peak strongly, with an abundance of sunspots, or it might be weaker, with fewer spots and less magnetic activity. Part of the challenge lies in the Sun's internal magnetic dynamics. The Sun's magnetic field is generated deep within its core, and this magnetic field is what drives the solar cycle. The exact workings of the Sun's internal magnetic dynamo, which generates and sustains the Sun's magnetic field, are still not fully understood. We know that it is caused by the movement of electrically charged gases in the Sun's interior, but the details of how this dynamo works, particularly the exact processes that lead to sunspots and flares, remain unclear. The dynamo process itself involves the convective motion of the Sun's hot gases, creating currents of charged particles that generate the Sun's magnetic field. This field fluctuates over time, leading to the regular waxing and waning of solar activity. However, While we can measure the magnetic fields on the surface of the Sun and observe sunspots, there's still a lot we don't understand about what triggers these fluctuations. For instance, we're unsure about the role of the Sun's equator compared to its poles in driving these magnetic changes, and how exactly magnetic fields can become twisted and tangled to produce the events we observe, like solar flares and CMEs. While the solar cycle has an average duration of about 11 years, the time between the solar minimum and maximum can vary. In some cycles, the Sun has experienced periods of unexpected calm, while in other cases, there have been extraordinarily active cycles. The cycle we're currently in, Solar Cycle 25, has been notably more difficult to predict. One significant challenge in predicting the cycle's intensity is that we don't fully understand how solar activity is linked to the Sun's long-term behavior. Over time, the Sun has displayed different levels of activity, with some periods of very low sunspot counts. This phenomenon is known as grand minima, and one of the most famous examples is the Maunder minimum, a period in the 17th century when the Sun had very few sunspots and was much quieter. We still don't know what causes these grand minima, or whether they will happen again in the future. Some researchers speculate that these periods of low activity could be tied to a variety of factors, including changes in the Sun's internal dynamics or changes in its interaction with interstellar space. The fact that we cannot easily predict solar activity has real-world consequences. Solar flares and CMEs are capable of causing immense disruptions to our technological infrastructure. A massive solar flare, for example, can overload electrical power grids, knock out GPS satellites, or interfere with radio communications. As we become more reliant on technology, understanding and predicting solar activity becomes a critical issue. While solar scientists can track solar phenomena in real time, they're still not able to provide reliable predictions far in advance. One of the most concerning aspects of the Sun's unpredictability is its ability to suddenly release a large burst of energy. These explosive bursts can occur with little warning, making it difficult to prepare for potential impacts on Earth. If a massive CME were to hit Earth head-on, it could lead to significant damage. Power grids could be knocked out for weeks or even months, and communication systems could be disrupted. It's also possible that astronauts on long-duration space missions or passengers on high-altitude flights could be exposed to higher levels of radiation during solar storms, which would require advanced shielding to protect them. Observatories, such as the Solar and Heliospheric Observatory and the Parker Solar Probe, have given us unprecedented views of the Sun's surface and interior. These spacecraft are helping to gather more data on the Sun's magnetic field, sunspots, and other solar phenomena. With better data, we can refine models of solar activity, improving our understanding of the solar cycle and its unpredictable nature. New computational techniques also aim to replicate the complex magnetic dynamics within the Sun's interior, attempting to predict how changes in the Sun's internal structure might affect solar activity. Still, as powerful as these models are, they are limited by the complexity of the Sun's magnetic fields and the difficulty of observing its interior directly. Despite the challenges, solar scientists are optimistic that, with more data and improved models, we'll eventually be able to predict solar cycles with greater accuracy. But for now, the Sun's behavior remains an unpredictable force that shapes life on Earth and in space, and one that continues to surprise us with its intensity, irregularity, and power. The mystery of the Sun's corona being hotter than its surface. One would naturally assume that the temperature of the Sun gets hotter as we move toward its core, and cooler as we approach the outer layers. After all, this is how most things in the universe behave: hotter at the center, cooler on the outside. But when it comes to the Sun, this simple rule of thumb doesn't apply. The temperature of the Sun's outer layer, the corona, is millions of degrees hotter than the surface beneath it, the photosphere. This seemingly strange and baffling observation is one of the most perplexing mysteries in solar physics. The photosphere, or the surface of the Sun, is the layer we can directly observe with the naked eye, even though it is not technically a solid surface, but rather a layer where the sun's energy starts to become visible. This layer has a temperature of about 5,500 degrees Celsius, or around 10,000 degrees Fahrenheit, which is incredibly hot by our standards, but far cooler compared to the temperatures in the sun's outer atmosphere, the corona. Surprisingly, the corona has a temperature that ranges between 1 to 3 million degrees Celsius, hundreds of times hotter than the photosphere below it. This temperature discrepancy is enormous, and it defies our basic understanding of heat transfer. According to traditional physics, the sun's atmosphere should cool off as it moves away from the core. After all, heat naturally radiates from hot to cold regions, and the sun's interior is far hotter than its outer layers. So, how can the corona be so much hotter than the surface of the sun, which is physically closer to the core? The sun's magnetic field is incredibly strong and complex, and it is believed to play a key role in heating the corona. The sun's surface is constantly shifting and churning due to the complex interactions of magnetic fields, creating loops and arches of magnetism that stretch out into the corona. These magnetic fields can trap and store vast amounts of energy, and under certain conditions, this energy is released in bursts, rapidly heating the surrounding plasma to extreme temperatures. Scientists believe that these magnetic reconnection events, when magnetic field lines come together and snap into new configurations, release vast amounts of energy that can heat the corona. This is a process called reconnection heating. The idea is that the magnetic fields on the sun are incredibly dynamic, constantly twisting and reconnecting in a complex dance. When these fields realign, they release energy in the form of heat, which could account for the extreme temperatures of the corona. Additionally, some researchers suggest that another form of energy transfer, called wave heating, might be at play. In this case, waves generated by the turbulence of the sun's inner layers travel outward into the corona. These waves could carry energy from the sun's interior to the corona, where they dissipate and raise the temperature. There are two primary types of waves that might contribute to this process: acoustic waves, which are essentially sound waves, and magnetohydrodynamic waves, ones that travel through the sun's magnetic field. These waves could carry enough energy to increase the temperature of the corona, although scientists are still studying how exactly they work. While both magnetic reconnection and wave heating are plausible mechanisms for heating the corona, the exact combination of these processes remains a topic of debate. The sun's corona is an incredibly dynamic and energetic environment, with constant fluctuations and movements. As researchers continue to gather data from spacecraft like NASA's Parker and the European Space Agency's Solar Orbiter, they hope to refine our understanding of how these processes work together to create the intense heat in the corona. One major challenge in solving the mystery is the lack of direct observation. The temperature difference between the photosphere and the corona is so great that studying the transition between the two regions is difficult. The corona is also incredibly diffuse compared to the dense interior of the sun, making it harder to study with traditional instruments. The outer layers of the sun, including the corona, are also constantly in motion, with CMEs and solar winds blasting outward, making observations even more complicated. Understanding the true nature of the sun's corona would not only help us understand the workings of our own star, but could also provide valuable insights into other stars across the universe, further enriching our understanding of the cosmos. And with that, the video must come to an end. But never fear, there are many more unexplained phenomena still left for us to cover. Comment down below if you'd like a follow-up on this topic, and if you enjoyed the video, consider leaving a like and subscribing. Thanks for watching.